The vital information was released at 7:47 in the morning Eastern Time on the 29th of October, 2025. David Finocchia, a specialist in spacecraft navigation at NASA's Jet Propulsion Laboratory, compiled a document that would profoundly shake observatories across the entire planet. 3I Atlas, the cosmic traveler we've been charting for months, is no longer conforming to gravitational pulls. It is accelerating directly away from the Sun at a rate of 135 kilometers per second squared and transversely at 60 kilometers per second squared. While these figures may seem modest, they are concrete, verified observations. If this celestial body is indeed a natural comet, then within the upcoming 30 days, it is predicted to shed 10% of its total mass. 10% represents 5.5 billion tons of material expected to erupt into space, creating a nebulous cloud so immense that every telescope, from our location to Jupiter, should readily detect its brilliant passage through our solar system. However, what truly disturbs my sleep at 3 in the morning is this. What if we detect absolutely nothing? If this is your first time here, please engage the like button and consider subscribing. Both actions significantly aid this channel's growth. In the comment section, share your geographical location, the current time where you are, and whether you believe we are witnessing a monumental astronomical cover-up or an unprecedentedly misunderstood comet in history. The anomaly, measuring 4 arcseconds on October 29th, was anticipated to be entirely predictable. This marked perihelion, the comet's closest approach to the Sun. Every comet, every asteroid, every fragment of rock and ice that has ever traversed our solar system adheres to a trajectory dictated by gravity. This includes Newton's foundational laws and Einstein's refinements. The underlying mathematics are elegant, precise, and have been validated over centuries. By inputting parameters such as mass, velocity, and position, one can accurately determine an object's location at any future point, be it an hour, a day, or a month from now. The cosmos does not present us with unforeseen trajectories. It simply cannot. Gravity is an immutable, deterministic force, except 3I Atlas deviated from its predicted path by 4 arcseconds. 4 arcseconds might not sound substantial. It represents a minuscule fraction of a degree. Imagine holding a dime at arm's length. 4 arcseconds would roughly equate to the apparent width of a human hair viewed from across a football field. Astronomers routinely work with such infinitesimal angles. They are accustomed to a level of precision that can be bewildering to the general public. Nevertheless, the significance lies in this. At a distance of 203 million kilometers from the Sun, a 4 arcsecond discrepancy translates into a tangible spatial displacement. It signifies a measurable offset from the trajectory predicted by gravitational forces. Such an offset can only be attributed to a non-gravitational influence. The Atacama Large Millimeter Array, or ALMA, was the first instrument to detect this anomaly. ALMA, situated high in the Chilean desert, comprises 66 radio dishes operating in unison, capable of observing the cosmos at wavelengths imperceptible to the human eye. On October 29th, as 3I Atlas reached its perihelion, ALMA's operators observed an unusual deviation in the positional data. The object was not where the JPL ephemeris predicted it to be, specifically in its right ascension. Although the discrepancy was minor, it remained consistent across multiple observations. This was sufficient for David Finocchia, an expert in orbital mechanics and the trajectories of near-Earth objects, to flag it immediately. Finocchia has dedicated his career to calculating the paths of asteroids and comets. He holds a doctorate in mathematics from the University of Pisa and has spent years refining the models used to predict close approaches, potential impacts, and orbital shifts. When he submitted his report to the JPL Small Body Database, he was not engaging in conjecture. He was documenting an observed phenomenon. Two components of acceleration were detected: a radial component directed precisely away from the Sun and a transverse component perpendicular to the Sun's direction. Both were real and necessitated an explanation. For a comet, the presumed explanation is straightforward. As the nucleus heats up, its volatile ices sublimate, transitioning directly from solid to gas. This includes water, carbon dioxide, and carbon monoxide. These gases are expelled outward from the surface, carrying dust and debris. The momentum of this ejected material exerts a reactive force on the nucleus itself, akin to a rocket engine operating in reverse. This phenomenon, known as the rocket effect, has been observed in hundreds of comets within our solar system. It is considered a natural and well-understood process. However, this is where the numerical data becomes alarming. The principle of momentum conservation is inviolable. If 3I Atlas is accelerating due to outgassing, then the mass of the ejected material multiplied by the velocity of that gas must equal the mass of the nucleus multiplied by its change in velocity. This equation can be rearranged to determine the rate at which the comet is losing mass. Avi performed this calculation, and the result is stark. If the acceleration measured by Finocchia originates from sublimation, then 3I Atlas is effectively evaporating with a half-life of approximately 6 months. 6 months. This implies that during the roughly 1 month it took to traverse the perihelion distance scale, it should have lost at least 1/16th of its total mass. 1/16th. The James Webb Space Telescope measured 3/2 Atlas's mass loss rate in the spring. It was 150 kilograms per second, a steady and continuous rate over 5 months. This rate of mass loss would not produce any detectable non-gravitational acceleration. Based on this, Low and his team calculated that the nucleus must weigh at least 33 billion tons. This is a colossal object, larger than any previously observed interstellar visitor, surpassing Oumuamua by a factor of 1 million and Borisov by a factor of 1,000. 33 billion tons is an immense quantity of ice and rock, and 1/16th of that amounts to 5.5 billion tons. 5.5 billion tons of gas and dust that should currently be erupting into the space surrounding 3I Atlas, forming a coma so expansive and luminous that it would be impossible to overlook. Consider the sheer magnitude of 5.5 billion tons in space. Imagine every structure in New York City, every vehicle, every bridge, every subway line, all pulverized into dust and propelled into the void at hundreds of meters per second. That is the scale we are discussing. A plume of material that would dwarf the nucleus itself, glowing under the sun's illumination, scattering photons, and emitting spectral lines from ionized gas. This is the kind of spectacle that amateur astronomers could capture from their own backyards. The European Space Agency's JUICE spacecraft, currently en route to Jupiter, is scheduled to pass within 64 million kilometers of 3I Atlas on November 4th. JUICE is not designed for comet observation. Its purpose is to explore Jupiter's icy moons, search for subsurface oceans, and map its magnetic fields and radiation belts. However, it is equipped with cameras and spectrometers. If a substantial cloud of gas surrounds 3I Atlas, JUICE will undoubtedly detect it. The geometrical alignment is ideal, the distance is sufficiently close, and the instruments are highly sensitive. Conversely, if JUICE observes nothing, if the images returned reveal a faint, compact nucleus devoid of any significant coma, no expanding shell of debris, and no indication of the catastrophic mass loss indicated by the non-gravitational acceleration, then we face a significant problem because the data does not lie. Either 3I Atlas is hemorrhaging material at a rate that should be blindingly evident, or the acceleration is not originating from sublimation at all. Low outlined this meticulously in his blog post on October 30th. He systematically presented the calculations, demonstrating his methodology, citing the Webb data, and referencing the JPL orbital fit. He avoided ambiguous language and refrained from hedging his conclusions with tentative phrases. He stated unequivocally that if we do not observe a massive gas cloud in November and December, then the non-gravitational acceleration cannot be attributed to cometary evaporation. And if it is not evaporation, then what remains? This is where the discussion becomes uncomfortable for many astronomers. Low has encountered a similar situation previously with Oumuamua. That initial interstellar visitor also exhibited non-gravitational acceleration. However, the Spitzer Space Telescope searched for the accompanying gas and dust. It found nothing, not a trace. Oumuamua accelerated without leaving any visible trace. Comet experts devised a new classification to address this: dark comet. This term describes a comet that does not produce a visible coma or tail, but still outgasses sufficiently to alter its trajectory. Low has pointed out, with his characteristic directness, that labeling such an object a dark comet is akin to calling a cave dweller's mobile phone a shiny rock. It is a descriptor that sidesteps the more challenging question. If an object accelerates without generating the gas that ostensibly causes that acceleration, perhaps it is not a comet at all. 3I Atlas was expected to be different. It possesses a coma and a tail. The Hubble Space Telescope imaged it in July, revealing a teardrop-shaped envelope of dust trailing the nucleus. Ground-based telescopes detected spectral signatures of cyanide, nickel, and hydroxyl radicals. It presented as a comet, and initial assessments suggested it behaved as one. This led to a collective sigh of relief. Interstellar objects, it seemed, could be conventional. Oumuamua, after all, was an anomaly. 3I Atlas was anticipated to demonstrate that interstellar comets behave much like their solar system counterparts, with variations primarily in their chemical composition due to their formation around different stars. However, we now have the 4 arcsecond deviation. We have the measured acceleration. We have the mass loss calculations screaming that something is fundamentally amiss. And we are on the verge of discovering whether the universe operates according to the principles we believe we understand, or if it has been attempting to convey a message all along, a message we have been too obstinate to receive. November and December will provide the answer. JUICE will commence its observations on November 4th. Ground-based telescopes will have their opportunity as 3I Atlas emerges from behind the Sun in mid-November. Hubble and Webb are also scheduled. The entire IAWN campaign, the International Asteroid Warning Network, is mobilizing observatories worldwide to track this object with unprecedented coordination. They are treating this situation akin to a planetary defense drill, which is a diplomatic way of stating their urgent need to ascertain the precise nature and behavior of this entity. On December 19th, 3/2 Atlas will achieve its closest approach to Earth, at a distance of 269 million kilometers. While still distant and posing no threat, this proximity will allow every major telescope to obtain a clear observation. If a plume is present, we will see it. If a coma is expanding at the rate indicated by the mass loss, we will measure it. If spectral analysis reveals the chemical fingerprints of significant sublimation, we will catalog them. And if nothing is observed, if 3I Atlas continues its silent, compact drift through space, accelerating without any apparent cause, then Avi's question becomes impossible to disregard. What if the non-gravitational acceleration is not merely a byproduct of heating and sublimation? What if it is an intentional act? What if an internal mechanism within the object is actively firing, executing course corrections, and utilizing the Sun's gravity for a precisely calculated orbital maneuver? 4 arcseconds. That is all it took. 4 arcseconds to transform October 29th from a routine perihelion passage into the most intensely scrutinized moment in the history of interstellar object studies. 4 arcseconds to compel every astronomer on the planet to pause and confront the question they have been evading since July. What if 3I Atlas is not what we believe it to be? Finocchia's report is publicly accessible. You can verify it yourself within the JPL Small Body Database under the entry for 3.2 Atlas. Scroll down to the non-gravitational parameters section. They are readily available there. Radial acceleration, transverse acceleration, these are numerical values with associated uncertainties and error bars, the kind of data typically published in peer-reviewed journals, meticulously verified by independent teams, and incorporated into the permanent scientific record. This is not speculation. It is not sensationalist reporting. It is navigation data from one of NASA's most esteemed experts in orbital mechanics, and it states, in the unambiguous language of mathematics, that 3.2 Atlas is not following a purely gravitational trajectory. The central question is not whether the acceleration is real, but rather what is causing it. And within the next few weeks, we will receive an answer. Either we will witness the plume, and 3I Atlas will be remembered as an exceptionally volatile interstellar comet with extreme sublimation rates and fascinating chemistry, or we will not observe the plume. In that scenario, every assumption we have made about this object, every comforting explanation, every reassuring press release will crumble. Because if an object approximately 5.6 kilometers in diameter can accelerate through space without ejecting billions of tons of gas, then it must be engaged in an activity for which we have no natural explanation. An activity that requires energy, control, and precision, something that appears far less like geology and far more like engineering. The countdown has begun. JUICE will commence its observational phase in 6 days. Ground-based telescopes will have their opportunity in 2 weeks. Hubble and Webb are already scheduled for December. The data is forthcoming, and upon its arrival, one way or another, we will have our answer. But here is the detail that causes me to lose sleep, the aspect that chills me when I contemplate it for too long. The timing. 3I Atlas reached perihelion on October 29th. This is the optimal moment for a spacecraft to engage its engines. This is known as the Oberth effect. When deeply embedded within a gravitational well, moving at peak orbital velocity, any applied thrust is significantly amplified by the existing kinetic energy. This is fundamental astronautics. If the objective is to alter trajectory, increase or decrease speed, or change direction, it is most efficiently accomplished at perihelion when closest to the Sun. And 3I Atlas executed this maneuver precisely as expected, right on schedule, at the very moment dictated by the physics. Was it mere coincidence? Did the ice happen to sublimate with such intensity at precisely the opportune moment to generate a measurable acceleration during the single window where such an acceleration would be most efficacious? Or did an internal mechanism within the object possess the exact timing to activate? The 4 arcsecond deviation is not simply a measurement. It is a question mark etched into the trajectory of an object that has already defied all our preconceived notions. And the answer, whatever it may prove to be, is hurtling towards us at 61 kilometers per second. November 4th, 6 days from now. JUICE will reveal what truly resides out there, and after that, there will be no turning back, no more conjecture, no more debate, only data. And whatever that data discloses about the nature of the third interstellar visitor to have crossed our threshold, bluer than the Sun. The coronagraphs captured something utterly impossible on October 30th. Multiple spacecraft, strategically positioned at various points throughout the solar system, all recorded the identical anomaly. 3I Atlas, during its passage through perihelion, shifted its spectral output towards wavelengths bluer than the Sun itself. Not a subtle shift, not a marginal difference, but a distinct, measurable, and inexplicable blueness. This phenomenon should never occur with any natural comet ever observed by humanity. Qichang Zhang and K.L. Batams published their findings within hours of processing the data. Their paper, submitted to Astrophysical Journal Letters, includes photometric data from 4 separate instruments: the stereo Secchi cameras, encompassing both the Hi-1 heliospheric imager and the COR2 coronagraph, SOHO's LASCO C3, the workhorse of solar observation for nearly 3 decades, and GOES 19's CCR1, the most recent addition to space-based coronagraph arrays launched just last year for operational space weather monitoring. 4 independent instruments, 4 distinct vantage points, and 4 sets of data, all presenting the same observation. 3I Atlas rapidly intensified in brightness as it approached perihelion, and its light exhibited a blue shift. The color measurements are remarkably precise. LASCO is equipped with multiple filters including blue, orange, deep red, and infrared, in addition to its standard clear filter. When they aggregated all the blue filter images of 3I Atlas, the comet appeared 0.7 magnitudes brighter than it did through the clear filter. 0.7 magnitudes translates to nearly twice the brightness. In the orange filter, it remained 0.4 magnitudes brighter than in the clear filter. The comet was emitting more light at shorter wavelengths, the opposite of what dust typically does to sunlight. CCR1 corroborated this finding independently. Its bandpass ranges from 470 to 740 nanometers, shifted approximately 40 nanometers bluer than LASCO's clear filter. This slight variation in wavelength sensitivity provided CCR1 an advantage in detecting the blue emission. The comet registered 0.44 magnitudes brighter in CCR1 compared to LASCO's clear filter. Different spacecraft, different orbits, yet the same outcome. Herein lies the significance. Dust particles scatter light. This is a fundamental and consistent property. When sunlight strikes a dust particle, the shorter blue wavelengths are scattered more efficiently than the longer red wavelengths. This is known as scattering. It is the same physical principle that renders Earth's sky blue and produces red sunsets. Dust particles tend to make objects appear redder, not bluer. Every comet ever observed, from the magnificent naked-eye comets to the faintest telescopic smudges, has demonstrated this reddening effect. The dusty coma reflects sunlight, but this reflection is shifted towards longer wavelengths. 3I Atlas exhibited the contrary behavior. It outshone the sun. The only mechanism capable of producing such a spectral shift is emission, not reflection. Hot gas emits light at specific wavelengths corresponding to the energy transitions of its constituent atoms and molecules. Ionization excites atoms into higher energy states, and when they return to their ground state, they release photons. Cyanogen, Cn, emits in the violet spectrum. Diatomic carbon, C2, famously known for its swan bands, glows green. The amino radical NH2 also contributes emissions in the blue and near ultraviolet regions. However, there is a confounding factor when invoking gas emission to explain the blue coloration. The instruments that detected this phenomenon were not specifically designed for gas analysis. Stereo's Hi-1 and COR2 possess bandpasses that largely miss the C2 swan bands. Hi-1 operates approximately from 595 to 720 nanometers, with some minor leakage into the blue and infrared. COR2 covers 670 to 750 nanometers. Both are shifted too far towards the red spectrum to efficiently capture C2 emissions. Yet both instruments indicated that the comet was brightening more rapidly than anticipated. LASCO's blue filter effectively captures C2 emissions, as does CCR1's broader bandpass. The observation of the comet being brighter in blue by these instruments is consistent with the presence of gas emission. However, Hi-1 and COR2 should not have been so sensitive to it unless the gas emission was extraordinarily intense, to the point where even the redward tail of the spectral lines was sufficiently bright to overpower dust scattering, or unless an alternative source was producing the blue light. Yang and Batams meticulously analyzed the brightness evolution. They adjusted for the comet's distance from Earth, accounted for the phase angle, and fitted the heliocentric dependence. The resulting exponent is astonishing. 3I Atlas brightened with distance from the Sun to the power of negative 7.5 plus or minus 1. In simpler terms, as the comet approached the Sun, its brightness increased at a rate described by 1 over the distance raised to the power of 7.5. Most Oort cloud comets, those distant visitors from the outer reaches of our solar system, exhibit brightening power laws between 2 and 4. An exponent of 2 would signify that brightness scales directly with the amount of sunlight incident on the surface, indicating no activity beyond simple reflection. An exponent of 3 or 4 suggests moderate sublimation, with gas production increasing as temperature rises. However, an exponent of 7.5 is not moderate. It is explosive. It indicates runaway sublimation, or a phenomenon so convincingly similar that it is indistinguishable. The paper's conclusion is carefully worded. The cause of 3I Atlas's rapid brightening remains unclear. The authors acknowledge that the observed rate significantly exceeds what is typically expected for Oort cloud comets at comparable distances. They highlight the blue color, the gas emission, and the unusual spectral characteristics. They propose a hypothesis. Perhaps carbon dioxide sublimation suppressed water, ice sublimation at greater distances, and now closer to perihelion, the water ice is finally dominating and erupting violently. However, they do not commit to this explanation, as the data does not entirely align. The brightness curve is excessively steep, the blue shift is excessively pronounced, and the entire event appears to be occurring at an intensity level that should be impossible for an object of this size at this distance. Let us delve into the actual meaning of the blue color. Spectroscopic analysis suggests that the surface of 3I Atlas is red. Tholins, complex organic molecules formed by the radiation processing of simple ices, coat the nucleus. Tholins are typically dark reddish-brown, resembling ancient ice exposed to cosmic rays for eons. They are adept at capturing blue light. This should render the comet a deeper shade of red than if it were merely composed of ice. The presence of observable blue light suggests its generation originates from within the coma, rather than simply being a reflection off the surface. Gas molecules, when excited by the sun's ultraviolet radiation, radiate at their specific spectral lines. This is a standard occurrence. Every active comet develops a gaseous coma, though its intensity is a key factor. The balance between gas emission and the scattering of light by dust determines the comet's overall hue. For Comet 3 Atlas to appear bluer than the Sun itself, the gas emission must be overwhelmingly dominant, completely obscuring the contribution from dust. Jacques Crozier and his colleagues at the Paris Observatory utilized radio telescopes to detect oxygen emission from 3I Atlas. The hydroxyl radical, OH, is a byproduct of water. As water molecules depart the nucleus and are exposed to solar ultraviolet rays, they dissociate into hydrogen and oxygen atoms. The oxygen atoms then emit radio waves at specific frequencies. Crovizier's team measured the rate of OH production between the 13th and 19th of October, just prior to the comet's closest approach to the Sun. The rate was calculated at 5.7 times 10 to the power of 28 molecules per second, with a margin of error of approximately 10%. For comparison, the last optical measurement of OH before 3I Atlas vanished behind the Sun occurred on September 12th at an astronomical unit distance of 2.19 from the Sun. At that time, the production rate was 10 to the power of 27.15 molecules per second. Now, the rate has risen to 10 to the power of 28.76, approximately 40 times greater. In the span of 1 month, the rate of OH production has increased 40-fold. The power law relating these two measurements exhibits an exponent of 8.3, indicating an even steeper increase than the comet's overall optical brightness. If this OH production is indeed indicative of water sublimation, then its escalating rate suggests that water is being released at a pace exceeding that of dust. This would account for the observed bluer hue and explain why the LASCO Blue and CC1 instruments registered the comet as significantly brighter than anticipated. However, this also brings us back to the issue of mass loss. If water is sublimating at the rate implied by the OH measurements, then 3I Atlas is shedding billions of tons of material. The resulting plume should be immense, with the coma expanding, radiating, and filling the field of view with scattered and fluorescent light. The CC1 instrument did indeed resolve the comet as an extended source, with stacked images revealing a fuzzy sphere approximately 4 arc-minutes in diameter, in contrast to a nearby star that appeared as a point. At a distance of 235 million kilometers, 4 arc-minutes translates to a physical diameter of roughly 270,000 kilometers. The coma is substantial, real, and extended. But is it large enough? Is it luminous enough? Does it align with the loss of 16% of the nucleus's mass over a single month? We will not have definitive answers until the JUICE mission arrives, or until ground-based telescopes can observe 3I Atlas against a dark sky, free from the sun's glare. Further insights will come when the Hubble and Webb telescopes direct their mirrors toward this object and capture detailed exposures across all their spectrographs. What we do ascertain is that 3I Atlas's interaction with solar radiation is exceptionally intense. The surge in brightness is extreme, the spectral shift is profound, and its peak activity coinciding precisely with perihelion is textbook behavior for a spacecraft executing a maneuver, but entirely atypical for a comet. Comets are inherently chaotic. They do not activate or deactivate like light switches, nor do they synchronize their activity levels perfectly with their orbital mechanics. Yet, this is precisely what we are observing. An additional detail in the paper by Yang and Batam warrants attention. They observed that the phase angle during most of these observations was remarkably low, ranging between 1.7 and 10.4 degrees. The phase angle represents the angle formed by the Sun, the comet, and the observer. A low phase angle signifies that we are viewing the comet with the Sun positioned almost directly behind us, akin to observing a full moon rather than a crescent. Under such low phase angles, cometary tails can orient themselves in nearly any direction relative to our line of sight, particularly ion tails, which follow the solar wind's path rather than the purely anti-solar trajectory of dust tails. The CC1 images do not display a distinct tail, only the diffuse coma. However, the stacking process encompassed a 6-day period during which the sunward direction shifted by 125 degrees, as observed from GOES 19. Any structure aligned with the Sun would consequently become smeared out, and any ion tail tracking the solar wind would blur into the general coma. The authors explicitly acknowledge this phenomenon. The absence of a visible tail does not imply its non-existence. It merely indicates that the observational geometry and the stacking procedure rendered it undetectable. Nevertheless, the observation of such a compact structure accompanying an object exhibiting such pronounced activity is unsettling. Comets typically develop extensive tails as they approach the Sun. The most spectacular comets in history, such as Hale-Bopp, Yakutak, and McNaught, all displayed tails stretching across tens of degrees of the sky. Here we have 3I Atlas at perihelion, the moment of peak activity, and we are observing a coma but no dramatic tail formation. Perhaps it is a matter of geometry. Perhaps it is the ratio of dust to gas. It is possible that 3I Atlas is unusually deficient in dust, primarily emitting gas, and gas tails are less visible from certain vantage points. This is a possibility. However, the accumulation of such possibilities begins to raise questions. At what point do we transition from considering mere possibilities to questioning the validity of our fundamental assumptions? The blue coloration is an established fact. The brightness curve is a documented reality. The precise timing of its activity is also factual. The existence of an extended coma has been confirmed. Collectively, these observations paint a picture of an object undergoing intense activity at perihelion, precisely when and where a comet is expected to be most active. It all seems to align logically, with one significant exception: the implication that the comet must shed 5 billion tons of mass in the coming weeks. We are on the verge of discovering whether this prediction holds true. Zhang and Batam conclude their paper with a deliberately open-ended statement, asserting that the post-perihelion behavior of 3I Atlas remains uncertain. They suggest that a plateau in brightness is as plausible as a rapid decline. They advocate for continued observations to provide a more conclusive explanation for the comet's observed behavior. In essence, they are stating that the future trajectory is unpredictable. The data is anomalous. The underlying physics is not fully understood, and immediate intensified observation is crucial. The month of November will be decisive. The blue hue will either dissipate as 3I Atlas moves away from the Sun and its sublimation rate decreases, or it will persist. The coma will either expand into a vast, evident plume of gas and dust, or it will not. The brightness will either follow a predictable downward trend, or it will deviate. Should 3I Atlas re-emerge from behind the Sun in a compact state, still luminous, still accelerating, and exhibiting no discernible mass loss, then the blue light will cease to be a mere curious spectral detail and will instead become evidence of something else entirely, something that generates light independently of sublimation, something that glows blue due to extreme heat, ionization, or energetic processes not typically observed in natural comets. The coronagraphs have fulfilled their purpose by capturing this critical moment. Now, we await the interpretation of its significance. On October 29th, while 3I Atlas was traversing perihelion, concealed behind the Sun, a different kind of upheaval occurred on social media. Brian Cox, a physicist and prominent science communicator with a vast online following, declared he had grown weary of unsubstantiated speculation. He issued a statement that would ignite one of the most public and acrimonious disputes in contemporary astronomy. To be absolutely clear, Cox posted, "Given recent drivel online, Comet 3I Atlas is a comet made of carbon dioxide and water ices and bits of other stuff. It is entirely natural in origin. Its orbit is as expected, and it will whiz around the Sun and then disappear off into the galaxy again." Drivel. That was the word he selected. Not conjecture, not hypothesis. Drivel. He followed up the next day with another assertion. "I keep seeing AI-generated content of me popping up on YouTube. The general rule is that if I appear to say something that you agree with, and you are a UFO person, flat Earth person, or think Comet Atlas 3I is a spaceship, it's fake." UFO person, flat earther, spaceship believer. Three distinct categories, all placed on the same level of credibility. According to Brian Cox, entertaining the notion that 3I Atlas might be something other than a naturally occurring comet places one in the same company as those who believe the Earth is flat and that vaccines contain microchips. Avi Loeb responded on the same day. He did not engage in social media discourse. That is not his modus operandi. Instead, he published an entry on Medium, a platform he has utilized for numerous posts since July, methodically presenting data and posing challenging questions, while the broader astronomical community seemingly attempts to ignore him. A few reporters inquired about the strong declarations made by the science popularizer Brian Cox, Loeb wrote, who asserted with conviction that 3I Atlas is unequivocally a natural comet. I explained that Brian Cox has not authored a single scientific paper concerning 3I Atlas. He operates as a science communicator rather than a researcher actively engaged with the relevant scientific discourse surrounding 3I Atlas. In contrast, I have authored 11 scientific papers in recent months focusing on 3I Atlas, 11 papers versus 0. This is not a rhetorical device. It is a citation count. Loeb provided a comprehensive list of these papers, including links and astrophysics data system identifiers for verification by any interested party. These 11 peer-reviewed publications, some authored solely by him and others co-authored, all concentrate on 3I Atlas, encompassing its orbital dynamics, spectroscopy, mass estimations, kinematic origins, correlation with the WOW signal, and non-gravitational acceleration. Each paper is substantiated by data, and every assertion is grounded in measurements. Brian Cox's publication record pertaining to 3I Atlas is entirely vacant. Not a single paper, not a conference abstract, not a technical note submitted to the Minor Planet Center or the International Astronomical Union. Loeb did not stop there. Rather than resorting to sweeping generalizations, he suggested that Brian should be compelled to elucidate the 9 anomalies associated with 3I Atlas. Scientific truth is not determined by popularity contests, but by meticulous attention to data, particularly when that data exhibits anomalies. 9 distinct observations, not 1 or 2, 9 separate phenomena that do not readily conform to the natural comet hypothesis as easily as Cox's dismissive tweets imply. Loeb has meticulously documented all of these, calculated their statistical probabilities, and published the methodologies and findings within the scientific literature. Cox possesses a doctorate in particle physics. He was involved in the ATLAS experiment at CERN, which involved studying proton-proton collisions at energies sufficiently high to generate exotic particles. He holds a professorship at the University of Manchester. He has hosted BBC television programs, authored best-selling books, and conducted public speaking tours. He is brilliant, charismatic, and admired by millions who perceive him as the approachable face of science, the 21st century equivalent of Carl Sagan. However, he is not a specialist in comets. He is not an expert in orbital dynamics. He is not an observational astronomer who dedicates nights to telescopes, collecting spectral and photometric data. His expertise lies in high-energy physics and the behavior of subatomic particles under extreme conditions. While this knowledge is valuable and his work is important, it is not directly pertinent to the question of whether an interstellar object follows a natural trajectory or exhibits signs of technological origin. Similarly, Loeb is not a traditional comet expert. He is a theoretical astrophysicist, a former chairman of Harvard's astronomy department, and the director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. He has published over 1,000 papers on a diverse range of subjects, from black holes to the early universe to the potential habitability of exoplanets. He possesses a profound understanding of data analysis, orbital mechanics calculations, and the assessment of statistical significance in anomalous observations. Furthermore, he has led the Galileo project since the year 2020. This initiative, backed by multi-million-dollar funding, is specifically dedicated to the scientific search for evidence of extraterrestrial technology, employing rigorous scientific methodologies. It is not a fringe operation. It is funded by private donors and staffed by accredited scientists. Custom-built observatories at Harvard, Colorado, and California are utilized. The project's focus is not on capturing blurry images of UFOs with phone cameras, but rather on collecting calibrated multi-wavelength data on aerial phenomena and space objects exhibiting unusual characteristics. 3i Atlas squarely falls into this category, characterized by unusual properties and anomalous data that deviates from expected norms. When Loeb meticulously analyzes and publishes papers calculating the probability of 3i Atlas's trajectory aligning with the ecliptic plane purely by coincidence, or interpreting its sunward jet as an optical illusion, or questioning whether its nickel-to-iron ratio is consistent with a natural comet, he is not fabricating information. He is meticulously performing calculations, documenting his methodology, and inviting critical evaluation from fellow scientists who can either validate his findings or identify any errors. Brian Cox, conversely, did not examine these calculations. He did not engage with the data. He simply dismissed it as drivel and moved on. His millions of followers, reassured by his pronouncements, accepted that the unsettling hypothesis of alien involvement was merely internet fodder propagated by attention-seeking contrarians. However, the situation becomes more nuanced. Chris Lintott, an astronomer at Oxford known for his work in citizen science, also entered the discourse. Lintott, well regarded in his field, is best recognized for co-founding Galaxy Zoo and similar projects that enable public participation in genuine astronomical research. He serves as the editor of Research Notes of the American Astronomical Society, a journal that publishes concise updates and preliminary findings. In July, Loeb submitted a paper to this journal presenting a straightforward analysis of 3i Atlas's trajectory, its alignment with the ecliptic plane, and the statistical probability of such an alignment occurring randomly. The paper included a brief observation that, if the object were of technological origin, this alignment might be intentional, representing a navigational choice to facilitate planetary encounters. Lintott, in his editorial capacity, contacted Loeb and requested the removal of any mention of potential technological origin. He advised to simply delete that section, allowing discussion of statistics and trajectory, but prohibiting any reference to aliens, spacecraft, or the hypothesis of an artificial origin. Loeb declined, not due to an unwavering commitment to the alien hypothesis, but due to his dedication to scientific transparency. The paper was not asserting that 3i Atlas was definitively artificial. Rather, it was exploring the hypothetical trajectory of such an object if it existed. This was a conditional statement, a theoretical exploration, a type of inquiry scientists are expected to undertake when confronted with data that deviates from established models. Lintott remained firm, removed the section, or the paper would not be published. Loeb complied and removed the section. Subsequently, Loeb published a different paper, co-authored with others, titled, "Is the Interstellar Object 3i Atlas Alien Technology?" This title explicitly stated the hypothesis and was submitted to a different journal whose editors did not impose censorship on the question. This paper includes a disclaimer. We strongly emphasize that this is largely a pedagogical exercise with interesting discoveries and strange serendipities worthy of a record in the scientific literature. By far the most likely outcome will be that 3i Atlas is a completely natural interstellar object, probably a comet. And the authors await the astronomical data to support this likely origin. The authors acknowledge the high probability of a natural origin, the comet hypothesis, and await supporting data. Nevertheless, they maintain that posing the question and calculating the predictions of a technological hypothesis are valuable exercises. This allows for comparison between predictions and observations, enabling the identification of the model that best fits the data. This is the fundamental process of scientific inquiry, proposing hypotheses, deriving predictions, collecting data, and comparing the two. The hypothesis that withstands this rigorous testing, that makes the most accurate predictions and requires the fewest arbitrary adjustments to align with observations, is the one provisionally accepted until superior data or theoretical frameworks emerge. However, this ideal scientific process is not currently being applied to 3I Atlas. Instead, two distinct camps have formed. One camp firmly asserts that it is unequivocally a comet. Any suggestion to the contrary is dismissed as pseudoscience, with the conviction that alternative explanations are unnecessary because the answer is already known. The opposing camp advocates for maintaining an open mind to all possibilities, gathering as much data as possible, and allowing observations to reveal the truth, rather than predetermining conclusions based on preconceived notions or personal comfort levels. The first camp holds the numerical advantage. The majority of astronomers concur that 3I Atlas is almost certainly a comet. Most press releases identify it as such, and public discourse generally treats the matter as settled. In the vast majority of instances, this approach is appropriate. Most interstellar objects are indeed natural in origin, and most comets are simply comets. Prematurely jumping to extraordinary conclusions without extraordinary evidence constitutes poor scientific practice. However, the second camp's perspective holds merit as well. The evidence supporting 3I Atlas's classification as a normal comet is less robust than the confident pronouncements suggest. The anomalies are real, and the statistical probabilities are concerning. The fact that every proposed explanation necessitates invoking special circumstances, unique compositions, or rare geometric alignments begins to appear as though the hypothesis is being shielded by a series of ad hoc modifications rather than being directly supported by empirical data. Cox's dismissal was particularly stinging because it completely bypassed the substantive scientific issues. He failed to address the 9 anomalies, nor did he provide explanations for why the trajectory alignment is insignificant, or why the nickel abundance is perfectly natural, or why the solar jet is merely an optical illusion. He simply declared it drivel, and his authoritative stance as a public scientist was sufficient to convince millions that Loeb was mistaken. Loeb's response was measured but incisive. He did not engage in personal attacks against Cox, nor did he question his intelligence or his credentials in particle physics. He simply pointed out that Cox had not undertaken the specific research pertinent to this particular problem. Cox was commenting from the sidelines, a spectator rather than an active participant. In scientific endeavors, the individuals who conduct the research, gather the data, and publish the findings are those whose opinions carry genuine weight. Lintot's role, while more subtle, could prove even more detrimental. As an editor, he possesses the power to influence what is published and what is not. By pressuring Loeb to remove the technological hypothesis from a paper that was otherwise scientifically sound, he was not safeguarding the integrity of science. Instead, he was protecting the comfort of scientists who are disinclined to grapple with uncomfortable questions. This phenomenon occurs more frequently than the public is aware. Scientific journals are subject to biases, editors have personal preferences, and reviewers hold opinions regarding what constitutes legitimate research versus fringe speculation. These biases, preferences, and opinions collectively shape the publication and rejection landscape, creating a filter that allows certain ideas to pass while blocking others. This filtering process is not always based on the quality of data or the rigor of analysis, but rather on whether the conclusions align with the prevailing comfort levels of the scientific community. Loeb has been navigating such filtering mechanisms for years with Oumuamua, his research into alien technology, and the Galileo project. He is willing to pose questions that make his colleagues uncomfortable and to endure ridicule and professional opposition, because he believes these questions are fundamentally important. He contends that humanity owes it to itself to examine the universe without preconceived notions, to follow the data wherever it leads, even if it diverges from expectations. Cox and Lintott represent the opposing perspective in this debate. Their viewpoint emphasizes caution, conservatism, and skepticism towards extraordinary claims. They are concerned with public perception, maintaining credibility, and avoiding the provision of ammunition to conspiracy theorists and purveyors of pseudoscience. From their standpoint, Loeb's openness to the technological hypothesis is seen as reckless, dangerous, and irresponsible. Both perspectives possess valid points. Both parties are committed to scientific inquiry and seeking accurate conclusions. However, they hold fundamentally different views on the methodology to achieve these goals. This divergence, evident in public discourse across social media, blog posts, and media interviews, reveals a profound schism within the scientific community that extends beyond trivial matters. It concerns the very authorization to pose questions, the acceptability of specific hypotheses, and our genuine openness to novel discoveries versus a predetermined acceptance of what is deemed possible, with anything deviating from this framework being inherently invalid. The irony is that empirical evidence, not the pronouncements of individuals like Cox, Loeb, or Lintott, will ultimately arbitrate this dispute. The forthcoming observations of 3I 2023A3 Tsuchinshan Atlas on November 4th, supplemented by ground-based telescope data in mid-November and deep imaging from the Hubble and James Webb Space Telescopes in December, will either substantiate the natural comet hypothesis or refute it. The presence or absence of the plume and its correlation with observed mass loss will be definitively established by these measurements. Upon the arrival of this data, one perspective will be validated, while the other will be compelled to account for its unfounded certainty. This is the essence of scientific progression, formulating predictions, subjecting them to rigorous testing, and accepting the outcomes, even if they diverge from expectations. Nevertheless, the conflict persists in the interim, with Cox denouncing the situation as nonsensical, Loeb highlighting the scarcity of peer-reviewed research, and Lintott attempting to suppress inconvenient hypotheses. Meanwhile, millions observe, attempting to discern whom to trust, whom to believe, and who is genuinely practicing science versus merely chasing notoriety. Frustratingly, the truth is that all are engaged in scientific pursuits, albeit with differing priorities and varying tolerances for ambiguity. Cox aims to shield the public from unwarranted optimism and speculative pronouncements. Lintott seeks to uphold academic integrity and prevent academic journals from becoming conduits for unsubstantiated theories. Loeb endeavors to ensure that critical discoveries are not overlooked due to a reluctance to investigate. November 4th marks the commencement of the influx of new data, with 4 days remaining. Following this, the discourse will shift from personal animosities to factual evidence, from disputing the right to question to understanding the actual answers. Ultimately, 3I 2023A3 will resolve this debate not by definitively proving anyone right or wrong, but by providing sufficiently clear, robust, and unambiguous evidence that both sides will be compelled to acknowledge. Until then, the internal scientific discord continues, playing out across social media, blogs, academic papers, and press releases, while a celestial object 5 kilometers in diameter traverses the void, utterly oblivious to the human drama unfolding in its celestial wake. Perihelion, the perfect concealment. October 29th, 1147 Universal Time. Perihelion. The precise moment 3I 2023A3 achieved its closest proximity to the Sun, reaching a distance of 203 million kilometers, strategically positioned between the orbital paths of Mars and Earth. For a celestial body naturally behaving as a comet, this is merely a consequence of orbital mechanics. For an artificial craft, however, this represents a crucial juncture. The Oberth effect stands as one of astronautics' most ingenious principles. When traversing deep within a gravitational field, at peak orbital velocity, any applied propulsion is significantly amplified. The kinetic energy already possessed by the craft magnifies the efficiency of its engine burn. This may initially seem counterintuitive. One might assume the timing of rocket ignition is inconsequential, with a fixed amount of propellant yielding a predictable delta V. However, orbital mechanics operates on different principles. The energy augmentation derived from a burn is contingent not only on the thrust itself, but also on the velocity at the moment of application. Envision yourself on a bicycle descending a steep incline. You are already moving at a substantial speed. Now, you begin to pedal. Each pedal stroke adds to your existing momentum. Because you are already in rapid motion, this addition translates into a far greater increase in kinetic energy than if you had pedaled with the same effort at a slower speed. This concept is precisely what applies to spacecraft navigating gravitational wells. For 3I 2023-A3, perihelion represents the nadir of the gravity well, the point where solar gravity has accelerated it to its maximum velocity. It is at this juncture that any additional thrust, trajectory adjustment, or velocity modification exerts the most significant influence on its ultimate path. If maneuvering or altering its course through the solar system is intended, this is the optimal time for such actions, neither before nor after, but precisely at this moment. Coincidentally, it was at this very time that the non-gravitational acceleration was detected. Is this mere chance? Comets typically exhibit heightened activity near perihelion due to increased solar radiation and temperature, leading to peak sublimation rates. If 3I 2023-A3 is indeed a comet, it logically follows that the most pronounced outgassing effects would occur around its closest solar approach. All predictive models and observations of other comets corroborate this phenomenon. However, a disquieting detail emerges. The timing is exceptionally precise, not simply close to perihelion, but exactly at perihelion. Not days prior or subsequent, but precisely when a gravitational assist maneuver would be most effective. The probability of natural outgassing spontaneously intensifying to produce measurable acceleration at the exact opportune moment for a gravitational assist is remarkably low. While not impossible, nature does not synchronize its processes with human engineering schedules. It is sufficiently low to warrant contemplation and raise questions. Furthermore, another detail emerges, transforming this event from a mere coincidence into something that suggests deliberate design. 3I 2023-A3 reached perihelion while Earth occupied the diametrically opposite side of the Sun, a configuration known as solar conjunction. From our vantage point, the comet and the Sun appeared in nearly the same celestial region, separated by less than 3 degrees. Ground-based telescopes are incapable of observing an object in such close proximity to the Sun due to the overwhelming glare of daylight. Even observations conducted shortly after sunset or before dawn become infeasible when a target lies within approximately 15 degrees of the Sun. From October 21st to November 14th, 3I 2023-A3 remains effectively obscured from Earth's view. This period of 24 days, nearly an entire month, coincides with its peak activity, the most compelling physical phenomena, and the window where anomalous behavior would be most readily detectable. Was this trajectory preordained? Was there a calculation that determined an optimal path through the inner solar system, one that would facilitate a close solar pass for a gravitational assist while simultaneously positioning the object behind the Sun as viewed from Earth during a critical maneuvering phase? The mathematical complexity is not insurmountable. With knowledge of Earth's future position, the Sun's location, and control over its trajectory, such a precise alignment is achievable. The trajectory can be orchestrated to pass perihelion on the far side of the Sun relative to Earth's orbital position. This is a standard practice for mission planners designing solar observation spacecraft that require avoidance of Earth's radio interference during crucial data acquisition periods. While 3I 2023A3 had no need to circumvent Earth's radio emissions, strategically positioning itself behind the Sun during solar conjunction would effectively shield it from Earth-based optical observation during a critical propulsive maneuver. What is definitively known regarding events during perihelion? The space-based coronagraphs provided observations. Stereo A was positioned approximately 47 degrees ahead of Earth in its orbit, meaning that from Stereo's perspective, 3I 2023A3 was not obscured by the Sun, but rather visible to both the COR2 coronagraph and, earlier in September, the HI1 heliospheric imager. SOHO, situated at the Earth-Sun L1 Lagrange point, perpetually between Earth and the Sun, captured 3I 2023A3 in its LASCO C3 instrument during its transit across the coronagraph's field of view in mid to late October. GOES-19, in geostationary orbit around Earth, offered a similar yet distinct vantage point, with its SUVI-2 camera recording the comet between October 18th and 24th. 4 instruments deployed from 4 different locations, all designed for solar observation, not comet tracking, yet all capable of detecting bright celestial objects passing through their fields of view. Crucially, all 4 instruments recorded 3I 2023A3 during its perihelion passage, an event supposedly hidden from observation. Therefore, observational data does exist. While it does not comprise high-resolution imagery or detailed spectroscopic analysis, the type of data obtainable from a dedicated telescope continuously tracking the comet with optimized filters and integration times. It is sufficient to ascertain brightness, measure photometry, detect the presence of an extended coma, and confirm the object's existence and activity. The coronagraphs, however, were incapable of discerning fine details. They did not resolve the nucleus nor image any discrete structures, such as fragments breaking away or jets emanating from specific surface regions. The spatial resolution of these instruments is simply insufficient. The CCR1 camera, with its 19 arcsecond pixels, can barely distinguish between an extended object and a point source. LASCO C3 is even less resolved, with its 56 arcsecond pixels. These instruments are engineered to image the solar corona, vast structures spanning millions of kilometers. A nucleus measuring 5 kilometers across is infinitesimal in comparison. Consequently, we know that 3I 2023A3 brightened, developed an extended coma, and exhibited a shift towards a bluer color. However, we remain uncertain whether it fragmented, whether its rotation altered, or if discrete structures emerged, indicative of venting from localized areas rather than uniform sublimation across its entire surface. This uncertainty is problematic because such details are significant. A natural comet experiencing thermal stress at perihelion is prone to fracturing. The ice binding the nucleus together weakens as temperatures rise, and thermal expansion generates internal stresses. Rapid outgassing can dislodge portions of the surface. This phenomenon is not uncommon. Comet Shoemaker-Levy 9 famously fragmented into over 20 pieces before impacting Jupiter. Comet Schwassmann-Wachmann 3 fractured into numerous fragments during a close solar passage. Fragmentation is a predictable consequence when comets approach the Sun too closely, exceeding the structural integrity of their icy matrices. If 3I 2023A3 underwent fragmentation, the coronagraphs may not have been able to detect it. Initially, the fragments would have remained in close proximity, appearing as a single unresolved object within the same patch of sky. Only later, as the fragments diverged along slightly different trajectories, would they become discernible as separate entities, a process that could take days or even weeks to become evident. If 3I 2023A3 remained intact throughout its perihelion passage, enduring 770 watts per square meter of solar irradiation while shedding billions of tons of mass through sublimation, it implies either an exceptionally robust structure for a cometary nucleus or a mass loss rate significantly lower than what the measured acceleration suggests. Both possibilities pose challenges to the natural explanation. Cometary nuclei are not renowned for their structural resilience. They are typically loosely bound aggregations of ice and rock, held together by weak gravitational forces and the cohesive properties of frozen volatiles. Elevated temperatures and subsequent ice evaporation tend to cause disintegration. The potential survival of 3I 2023A3 intact through perihelion, assuming it did, points either to an unusually strong internal structure or a composition dissimilar to typical comets. Alternatively, it suggests that the object's integrity is not derived from ice and gravity alone, but from something else entirely, something artificial, something engineered to withstand thermal and mechanical stresses without succumbing to disintegration. The answer will soon be forthcoming. As 3I 2023A3 emerges from behind the Sun in mid-November, ground-based telescopes will have their initial opportunity to observe its post-perihelion state. If fragmentation occurred, multiple objects will be visible where a single one previously existed. If it remained intact, a solitary nucleus will be observed, its size potentially altered depending on the mass lost, but fundamentally coherent and continuing along its established trajectory. JUICE will be the first to observe it on November 4th. The European Space Agency's Jupiter Icy Moons Explorer, currently en route to the outer solar system, carries a suite of instruments designed to study Europa, Ganymede, and Callisto, large icy moons that may harbor subsurface oceans conducive to life. While JUICE was not originally designed for comet observation, it is equipped with cameras, and 3I 2023A3 will pass within 64 million kilometers of the spacecraft's position. Although 64 million kilometers sounds like a considerable distance, in astronomical terms it is relatively close. This proximity should allow JUICE's instruments to resolve the coma, measure brightness, and collect spectral data if the comet is sufficiently luminous. The observational geometry is favorable, with a solar elongation exceeding 18 degrees from JUICE's perspective, placing it sufficiently far from the Sun's glare for feasible observations. Moreover, unlike Earth-based telescopes, JUICE will not be hindered by twilight or atmospheric turbulence. It possesses a clear view from space at a time when 3I 2023A3 should still be actively sublimating if the perihelion heating triggered significant outgassing. The observations from JUICE will serve to constrain the possible explanations. If the coma appears substantial, if the brightness remains high, and if spectral lines indicate ongoing gas production at rates consistent with the calculated mass loss, then the natural comet hypothesis will gain support. This would suggest that the observed acceleration originated from outgassing, as hypothesized, and that the object is behaving as expected for a volatile-rich nucleus near perihelion. Conversely, if the coma appears compact, if the brightness diminishes more rapidly than sublimation models predict, indicating a lack of the billions of tons of gas expected to surround the nucleus, then a significant problem arises. In such a scenario, the acceleration cannot be attributed to outgassing, necessitating an alternative explanation. The roster of such alternative explanations is regrettably short. Furthermore, the matter of the trajectory's evolution requires consideration. Did it change? The 4 arcsecond deviation detected by ALMA on October 29th confirms the presence of acceleration, but acceleration over a brief period does not necessarily imply a substantial alteration in trajectory. The magnitude, duration, and direction of the acceleration are crucial factors. Minor thrusts applied for short durations might result in a slight orbital perturbation, without drastically altering the overall path. Larger thrusts or sustained burns would produce more noticeable changes. JPL routinely updates its orbital element sets as new observational data becomes available. The current ephemeris for 3I 2023A3 within its 27th orbit incorporates the non-gravitational acceleration parameters provided by PGL Cox, Dr. Loeb, and Dr. Lintott all express a commitment to scientific rigor and the pursuit of truth. However, their fundamental disagreement lies in the methodology employed to achieve these aims. This contention, playing out publicly across social media platforms, blog posts, and interviews, has illuminated a profound rift within the scientific community, one that transcends mere disagreements. It concerns the very locus of inquiry, who is empowered to ask questions, what constitutes a valid hypothesis, and whether genuine openness to new discoveries prevails, or if preconceived notions dictate that anything outside established boundaries is inherently erroneous. The underlying irony is that empirical data, not the opinions of individuals, will be the ultimate arbiter. The observations of 3I 2023-A3 by JUICE on November 4th, followed by ground-based telescopes in mid-November and culminating in deep exposures by Hubble and Webb in December, will either corroborate the hypothesis of a natural comet or debunk it. The plume's existence and its correlation with measurable mass loss will be definitively ascertained. Upon the arrival of this data, one perspective will be vindicated, and the other will be obligated to explain its unwarranted confidence in an incorrect conclusion. This is the very essence of scientific advancement. Predictions are made, tested, and the results are embraced, irrespective of whether they align with initial desires. In the interim, however, the dispute intensifies. Cox decries the situation as irrational, Loeb points to the lack of published research, and Lintott attempts to suppress inconvenient hypotheses. Meanwhile, millions of observers are left to navigate the complex landscape, seeking to identify whom to trust, whom to believe, and who is practicing genuine science versus merely pursuing sensationalism. The frustrating reality is that all are engaged in scientific endeavor, albeit with differing priorities and varying tolerances for uncertainty. Cox seeks to safeguard the public from false hope and unfounded speculation. Lintott aims to uphold academic standards and prevent journals from becoming platforms for unverified theories. Loeb strives to ensure that significant discoveries are not overlooked due to an apprehension to explore. The arrival of the first new data on November 4th, marking 4 days from now, will initiate a shift in the debate. The focus will pivot from personalities to facts, from the authority to ask questions to the substance of the answers themselves. One way or another, 3I 2023A3 will settle this disagreement, not by definitively declaring anyone right or wrong, but by furnishing evidence so clear, so robust, and so unambiguous that both sides are compelled to acknowledge it. Until that juncture, the internal scientific conflict continues its public manifestation through tweets, blog posts, academic papers, and press releases, while a celestial object 5 kilometers in diameter hurtles through space, utterly indifferent to the human drama unfolding in its wake. The Perfect Haven, Perihelion, October 29th, 11:47 Universal Time, Perihelion. The precise moment 3I 2023A3 reached its closest proximity to the Sun, a distance of 203 million kilometers, perfectly situated between the orbital paths of Mars and Earth. For a natural comet, this alignment is merely a matter of orbital geometry. For an artificial spacecraft, however, this represents a pivotal opportunity. The Oberth effect is one of the most elegant principles in astronautics. When an object is deeply embedded within a gravity well, moving at its maximum orbital velocity, any applied thrust is significantly amplified. The kinetic energy already possessed by the object magnifies the effectiveness of its engine burn. This may initially seem counterintuitive. One might assume the timing of rocket ignition is irrelevant, as a fixed quantity of propellant produces a fixed delta V. However, orbital mechanics operates differently. The energy gained from a burn depends not only on the thrust itself, but also on the velocity at the moment of application. Imagine riding a bicycle down a steep hill. You are already traveling at a considerable speed. Now, you begin to pedal. Each pedal stroke adds to your existing velocity. Because you are already moving rapidly, this addition results in a much larger increase in kinetic energy than if you had applied the same pedaling effort at a slower speed. This principle is scaled up for spacecraft traversing gravitational fields. For 3I 2023A3, perihelion signifies the bottom of the gravity well, the point where solar gravity has accelerated it to its peak speed. It is at this juncture that any additional thrust, any course correction, or any velocity adjustment will have the greatest impact on its final trajectory. If maneuvering or altering its path through the solar system is intended, this is the optimal moment, not before, not after, but precisely now. It was at this very time that the non-gravitational acceleration was measured. Coincidence? Perhaps. Comets naturally tend to exhibit peak activity near perihelion due to the intensified solar flux and temperature leading to maximal sublimation rates. If 3I 2023A3 is indeed a comet, it logically follows that the most pronounced outgassing effects would manifest around its closest solar approach. All prevailing models predict this, and observations of other comets confirm it. However, a disquieting detail emerges. The timing is exceptionally precise, not merely close to perihelion, but exactly at perihelion. Not a few days prior or subsequent, but precisely when a gravitational assist maneuver would yield its greatest effectiveness. the likelihood of natural outgassing naturally intensifying to produce measurable acceleration at the exact moment optimal for a gravitational assist is exceedingly low. While not impossible, nature does not orchestrate its processes to align with human engineering timelines. It is sufficiently improbable to warrant careful consideration and questioning. Furthermore, another detail surfaces, transforming this event from a mere coincidence into something suggestive of deliberate design. 3I 2023A3 reached perihelion while Earth was positioned on the opposite side of the Sun, a configuration known as solar conjunction. From our perspective, the comet and the Sun appeared in nearly the same part of the sky, separated by less than 3 degrees. Ground-based telescopes are unable to observe an object situated so close to the Sun as the overwhelming glare of daylight renders them ineffective. Even observations conducted shortly after sunset or before dawn become impossible when a target lies within approximately 15 degrees of the Sun. From October 21st to November 14th, 3I 2023, A3 is effectively invisible from Earth. This period of 24 days, nearly an entire month, coincides with its peak activity, the most significant physical phenomena, and the window where anomalous behavior would be most readily detectable. Was this trajectory intentionally planned? Was there a calculation that identified an optimal path through the inner solar system, one that would facilitate a close solar pass for a gravitational assist while simultaneously positioning the object behind the Sun as viewed from Earth during a critical maneuvering phase? The mathematical complexity involved is not prohibitive. With knowledge of Earth's orbital position and the Sun's location, and with control over its own trajectory, such precise alignment is achievable. The path can be engineered to pass perihelion on the far side of the Sun relative to Earth's orbital position. This is a common practice for mission planners designing solar observation spacecraft that require avoidance of Earth's radio interference during crucial measurement periods. While 3I 2023A3 had no such requirement to avoid Earth's radio signals, positioning itself behind the Sun during solar conjunction would effectively obscure it from Earth-based optical telescopes during a critical propulsive burn. What is definitively known about the events surrounding perihelion? The space-based coronagraphs provided observations. Stereo A was positioned approximately 47 degrees ahead of Earth in its orbit, meaning that from Stereo's perspective, 3I 2023A3 was not obscured by the Sun, but rather visible to both the COR2 coronagraph and, earlier in September, the HI-1 heliospheric imager. SOHO, located at the Earth-Sun L1 Lagrange point, constantly positioned between Earth and the Sun, captured 3I 2023A3 in its LASCO C3 instrument as the comet traversed its field of view in mid to late October. GOES 19, in geostationary orbit around Earth, offered a similar but slightly different vantage point, with its SUVI-2 camera recording the comet between October 18th and 24th. 4 instruments deployed from 4 distinct locations, all designed to study the Sun, not comets, yet all capable of detecting bright objects that happen to pass through their fields of view. Crucially, all 4 instruments recorded 3I 2023A3 during its perihelion passage, an event that was supposedly obscured from observation. Therefore, observational data does exist. While it does not consist of high-resolution imagery or detailed spectroscopic analysis, the type of data obtainable from a dedicated telescope continuously tracking the comet with optimized filters and integration times. It is sufficient to determine brightness, measure photometry, detect the presence of an extended coma, and confirm the object's existence and activity. The coronagraphs, however, were incapable of discerning fine details. They did not resolve the nucleus, nor did they image any discrete structures, such as fragments detaching or jets erupting from specific surface regions. The spatial resolution of these instruments is simply insufficient. The CCR1 camera, with its 19 arcsecond pixels, can barely differentiate between an extended object and a point source. LASCO C3 exhibits even coarser resolution with its 56 arcsecond pixels. These instruments are engineered to image the solar corona, immense structures millions of kilometers across. A 5-kilometer nucleus is microscopic in comparison. Thus, we know that 3I 2023A3 brightened, developed an extended coma, and exhibited a shift towards a bluer hue. However, we remain uncertain whether it fragmented, whether its rotation changed, or if discrete structures appeared, potentially indicating venting from specific locations rather than uniform sublimation across its entire surface. This uncertainty is problematic because such details are significant. A natural comet undergoing thermal stress at perihelion is prone to fracturing. The ice that binds the nucleus together weakens as temperatures rise, and thermal expansion generates internal stresses. Rapid outgassing can dislodge portions of the surface. This is not an uncommon occurrence. Comet Shoemaker-Levy 9 famously fragmented into over 20 pieces before impacting Jupiter. Comet Schwarzmann-Wachmann 3 split into numerous fragments during a close solar passage. Fragmentation is a normal, expected outcome when comets approach the Sun too closely, and their structural integrity cannot withstand the increased heating. If 3I 2023A3 fragmented, the chronographs may not have been able to detect it. Initially, the fragments would have remained clustered together, still appearing as a single, unresolved object within the same patch of sky. Only later, as the fragments diverged along slightly different trajectories, would they become discernible as separate entities, a process that could take days or even weeks to become evident. If 3I 2023A3 remained intact throughout its perihelion passage, enduring 770 watts per square meter of solar irradiation while losing billions of tons of mass through sublimation, it implies either an exceptionally robust structure for a cometary nucleus or a mass loss rate significantly lower than what the measured acceleration suggests. Both scenarios pose challenges to the natural explanation. Cometary nuclei are not known for their structural integrity. They are typically loosely bound aggregations of ice and rock, held together by weak gravitational forces and the cohesive properties of frozen volatiles. Elevated temperatures and subsequent ice evaporation tend to cause disintegration. The potential survival of 3I 2023A3 intact through perihelion, assuming it did, points either to an unusually strong internal structure or a composition dissimilar to typical comets. Alternatively, it suggests that the object's integrity is not derived from ice and gravity alone, but from something else entirely, something artificial, something engineered to withstand thermal and mechanical stresses without disintegrating. The answer will soon be forthcoming. As 3I 2023A3 emerges from behind the Sun in mid-November, ground-based telescopes will have their initial opportunity to observe its post-perihelion state. If fragmentation occurred, multiple objects will be visible where a single one previously existed. If it remained intact, a solitary nucleus will be observed, its size potentially altered depending on the mass lost, but fundamentally coherent and continuing along its established trajectory. JUICE will be the first to observe it on November 4th. The European Space Agency's Jupiter Icy Moons Explorer, currently en route to the outer solar system, carries a suite of instruments designed to study Europa, Ganymede, and Callisto, large icy moons that may harbor subsurface oceans conducive to life. While JUICE was not originally designed for comet observation, it is equipped with cameras, and 3I 2023A3 will pass within 64 million kilometers of the spacecraft's position. Although 64 million kilometers sounds like a considerable distance, in astronomical terms, it is relatively close. This proximity should allow JUICE's instruments to resolve the coma, measure brightness, and collect spectral data if the comet is sufficiently luminous. The observational geometry is favorable, with a solar elongation exceeding 18 degrees from JUICE's perspective, placing it sufficiently far from the Sun's glare for feasible observations. Moreover, unlike Earth-based telescopes, JUICE will not be hindered by twilight or atmospheric turbulence. It possesses a clear view from space at a time when 3i 2023A3 should still be actively sublimating if the perihelion heating triggered significant outgassing. The observations from JUICE will serve to constrain the possible explanations. If the coma appears substantial, if the brightness remains high, and if spectral lines indicate ongoing gas production at rates consistent with the calculated mass loss, then the natural comet hypothesis will gain support. This would suggest that the observed acceleration originated from outgassing, as hypothesized, and that the object is behaving as expected for a volatile-rich nucleus near perihelion. Conversely, if the coma appears compact, if the brightness diminishes more rapidly than sublimation models predict, indicating a lack of the billions of tons of gas expected to surround the nucleus, then a significant problem arises. In such a scenario, the acceleration cannot be attributed to outgassing, necessitating an alternative explanation. The roster of such alternative explanations is regrettably short. Furthermore, the matter of the trajectory's evolution requires consideration. Did it change? The 4 arcsecond deviation detected by ALMA on October 29th confirms the presence of acceleration, but acceleration over a brief period does not necessarily imply a substantial alteration in trajectory. The magnitude, duration, and direction of the acceleration are crucial factors. Minor thrusts applied for short durations might result in a slight orbital perturbation without drastically altering the overall path. Larger thrusts or sustained burns would produce more noticeable changes. JPL routinely updates its orbital element sets as new observational data becomes available. The current ephemeris for 3i 2023A3 within its 27th orbit incorporates the non-gravitational acceleration parameters provided by Finocchiaro. These parameters quantify the trajectory's deviation from pure gravitational influence. As more data becomes available from JUICE, ground-based telescopes, Hubble, and Webb, JPL will refine the orbital model, update the non-gravitational terms, and reveal whether the acceleration was a transient spike or a sustained phenomenon. If it was transient, lasting only a few hours or days around perihelion, it could be attributed to peak solar heating, a burst of sublimation, intense but short-lived, generating thrust for a limited duration before outgassing subsided to lower rates. This would align with natural cometary behavior, albeit at the extreme end of the spectrum. If, however, the acceleration was sustained, continuing for weeks before and after perihelion, it suggests a more controlled, deliberate action. This would imply something less akin to a comet passively responding to thermal input and more akin to a craft actively adjusting its course. The data will provide the answer. JPL's orbital fits will confirm this. The close Earth approach on December 19th will yield precise astrometric measurements that can be compared to pre-perihelion observations. Any deviation from the predicted path will be readily apparent. Trajectory alterations are imperceptible. Orbital mechanics is a field of extreme precision. If 3i 2023A3 maneuvered, we will know. However, for now, we exist within an observational gap. This 24-day period, during which the most significant object in the solar system is concealed behind the Sun, engaged in its unknown activities, remains invisible to the telescopes capable of distinguishing between reality and speculation. 4 days until JUICE's observation. 14 days until ground-based telescopes can reacquire it. 49 days until its closest approach to Earth, at which point every major observatory will be trained on 3i 2023A3, collecting data, measuring positions, and comparing observations to predictions. 49 days to determine whether perihelion was a routine passage through the inner solar system or the moment when an object from another star executed a meticulously planned gravitational assist, utilizing our Sun's mass to alter its trajectory in ways we are only beginning to comprehend. The perfect hiding place, whether by chance or by design. And very soon we will have the answer. The elusive mass cloud, 5.5 billion tons of gas. This is not a metaphor, it is not an approximation. It represents the minimum quantity of material that 3i 2023A3 must have ejected during its perihelion passage if the observed non-gravitational acceleration is indeed attributable to outgassing. This equates to 5,500 million tons. Written out, this is 5.5 multiplied by 10 to the power of 15 grams, or 5.5 petagrams. This is equivalent to the mass of approximately 50 billion average-sized automobiles, or a cube of ice roughly 2 kilometers on each side. This mass has vanished, vaporized, and been expelled into space by solar heating, dispersing outward from the nucleus at hundreds of meters per second, forming a cloud that should be discernible from Earth, from Mars, and from any spacecraft equipped with a camera pointed in the correct direction. Yet we have not observed it, and this is becoming problematic. The calculation is straightforward. Avi Loeb elucidated this on October 30th, the day following perihelion, and any individual with a background in physics can verify the figures. Momentum must be conserved. As gas molecules depart from the surface of a comet nucleus, they carry momentum with them. This momentum must originate from somewhere. It is derived from the nucleus itself, which recoils in the opposite direction, analogous to a rocket engine expelling exhaust. The mass times acceleration of the nucleus is equal to the rate of mass loss multiplied by the velocity of the ejected gas. Rearranging this equation yields the evaporation timescale, the time required to lose a significant fraction of the nucleus's mass. For 3i 2023A3, given the acceleration measured by Finocchiaro, this timescale is approximately 6 months. 6 months to lose half of its mass. 1 month to lose 1/16th of its mass. 1/16th of 33 billion tons is 5.5 billion tons. This is the quantity of gas that should currently surround 3i 2023A3. Not might be, but should be. The principles of physics necessitate it. If the acceleration is real and originates from outgassing, then the gas must be present. So, where is it? The James Webb Space Telescope measured a mass loss rate in the spring, prior to perihelion, when 3i 2023A3 was still several astronomical units from the Sun. This rate was 150 kilograms per second, steady and continuous over 5 months, accumulating to billions of kilograms. However, this mass loss was spread over such an extended period and occurred at such a low rate that it did not produce a measurable non-gravitational acceleration. The gas dispersed gradually, forming a tenuous coma detectable by spectroscopy, but it did not overwhelm the reflected sunlight from the nucleus. Now, post-perihelion, the mass loss rate should be vastly higher. The acceleration data implies a rate thousands of times greater than what Webb observed. At such a rate, the gas should no longer be tenuous. It should be dense, bright, and conspicuous. Consider the visual impact of 5 billion tons of water vapor in space. Water molecules, H2O, have a molecular weight of 18. Therefore, 5 billion tons corresponds to approximately 1.7 multiplied by 10 to the power of 32 molecules. That is 10 to the 32nd, or 100 million trillion water molecules. If these molecules dissociate into hydroxyl radicals and hydrogen atoms under solar ultraviolet radiation, as they do almost immediately, The result is twice as many hydroxyl radicals, approximately 3 multiplied by 10 to the 32nd O molecules, each fluorescing at characteristic wavelengths in the ultraviolet and radio spectrum. Jacques Provizier's radio observations detected O production in mid-October. The rate he measured, 5.7 multiplied by 10 to the 28th molecules per second, was already high. But this represented cumulative production over some averaging period, likely hours or days, depending on the radio telescope's integration time. The total quantity of O molecules present within the coma at any given instant is dictated by its production rate and its photodissociation lifespan. This lifespan refers to the duration it takes for solar ultraviolet radiation to cleave the O into its constituent oxygen and hydrogen atoms. At an orbital distance equivalent to 1 astronomical unit from the Sun, O possesses a lifespan of approximately 160,000 seconds, which equates to roughly 2 days. Proximity to the Sun, however, significantly reduces this lifespan. At an aphelion distance of 1.36 astronomical units for the object designated 3I 2023A3 Tsuchinshan Atlas, its lifespan is notably shorter, estimated at around 140,000 seconds. Despite this reduction, it remains sufficiently long for a steady-state coma to form, containing an estimated 100 to the 33rd power molecules, assuming a production rate of 10 to the 28th power molecules per second. This constitutes a substantial and detectable cloud of hydroxyl radicals, which fluoresce under solar ultraviolet illumination, emitting photons and scattering light, thereby generating a visible halo surrounding the nucleus. Radio telescopes are expected to easily detect this phenomenon. Similarly, optical telescopes equipped with appropriate filters should also be capable of observing it. Ultraviolet spectrographs, in turn, ought to identify absorption or emission lines. This is not a subtle effect. It is a prominent and significant display. It represents billions upon billions of molecules vociferously announcing their presence across the electromagnetic spectrum. Nevertheless, as of October 30th, confirmation of its existence at the scale predicted by the observed acceleration remains elusive. We have the measurement from Crevier from mid-October, but this observation predates the object's perihelion, meaning it was slightly farther from the Sun and presumably less active at that time. We have not yet obtained post-perihelion measurements of O. The radio telescopes have not yet published their updated observations. Ground-based optical telescopes are currently unable to view 3I 2023A3 as it is positioned behind the Sun from Earth's vantage point. This is precisely where the JUICE mission becomes relevant. Scheduled for November 4th, just 4 days from now, this spacecraft is equipped with several instruments designed to detect the coma, should it exist. Janus, the optical camera system, is capable of imaging the comet and quantifying its brightness and spatial extent. UVS, the ultraviolet spectrograph, can detect O and other chemical species within the ultraviolet spectrum. MAGIS, the visible and infrared spectrometer, is designed to analyze the composition of the coma's gaseous material. If 3I 2023A3 is indeed enveloped by approximately 5 billion tons of sublimated material, JUICE will undoubtedly detect it. The geometric alignment is favorable for observation. JUICE will be positioned approximately 64 million kilometers from 3I 2023A3, a distance close enough to achieve adequate spatial resolution. The solar elongation from JUICE's perspective exceeds 18 degrees, which is sufficiently far to prevent interference from solar glare. The phase angle, defined as the angle between the Sun, the comet, and JUICE, will be relatively low. This means JUICE will be observing the sunlit hemisphere of the coma, where activity is anticipated to be most vigorous. If JUICE's cameras reveal a large, diffuse coma with an apparent size consistent with billions of tons of gas expanding at hundreds of meters per second, then the enigma will be resolved. 3I 2023A3 would be classified as a comet, albeit an exceptionally active and unusual one, but fundamentally a natural celestial body. The observed acceleration would be attributed to outgassing, and its blue coloration to gas emission. The entire scenario would then align with established cometary behavior. However, should JUICE's imagery depict a compact nucleus with only a faint, diminutive coma that is inconsistent with the substantial mass loss required to account for the measured acceleration, a significant discrepancy will arise. In such a case, the existing calculations would be invalidated, indicating that something else is imparting acceleration to 3I 2023A3 without producing the discernible observable signature expected from sublimation. As stated plainly by Lowe in his blog post on October 30th, if the extensive EON data fails to reveal a voluminous cloud of gas surrounding 3I 2023A3, then cometary evaporation cannot be considered a natural explanation for its non-gravitational acceleration. This leaves us with the question, what other mechanism could generate thrust without ejecting mass, or at least without ejecting a detectable quantity of mass? The options are exceedingly limited. One possibility is radiation pressure, acting upon an object characterized by low density and a large surface area. However, 3I 2023A3 is substantial, measuring at least 5 kilometers across and presumed to possess considerable density. Radiation pressure is effective on objects such as solar sails, which are thin films with an exceptionally high surface area to mass ratio, not on multi-billion-ton masses of rock and ice. Another consideration is solar wind momentum transfer. The solar wind, composed of charged particles, could theoretically exert a push against a conductive surface. However, the magnitude of this effect is minuscule, orders of magnitude too small to explain the observed acceleration. This would necessitate the presence of a magnetic field, providing a more efficient coupling mechanism between the solar wind and the object. While theoretically possible, this scenario requires specific conditions that are not typically found in natural comets. Alternatively, an engine involving internal propulsion or a reaction drive that expels reaction mass in a controlled, directed manner could be responsible. This would not necessarily be a conventional rocket. It could involve an ion drive, a plasma thruster, or perhaps something more exotic. But crucially, it would produce thrust without generating a massive, visible exhaust plume. Such a scenario sounds like science fiction, even absurd. Yet, if the gas cloud is demonstrably absent, and if JUICE returns images of a quiescent compact object that is accelerating nonetheless, then the absurd begins to appear as the only remaining plausible explanation. The hypothesis of the dark comet attempts to bridge this explanatory gap. By definition, a dark comet is an object that undergoes outgassing but fails to produce a visible coma or tail. This term was initially conceived to account for the behavior of 2I Oumuamua, which exhibited non-gravitational acceleration without any detectable gas or dust surrounding it. Spitzer observations of Oumuamua revealed nothing. Consequently, comet experts speculated that perhaps the gas was present, but did not generate a visible signature, possibly due to an extremely low dust-to-gas ratio or an unusual composition that rendered it undetectable by standard methods. Lowe has highlighted the logical inconsistency inherent in this concept. If a comet is defined by the presence of a visible coma and tail, then a dark comet is an oxymoron, akin to concepts like invisible light or silent sound. The coma and tail are the defining characteristics of a comet. Their absence leaves an object that accelerates without an apparent cause, which bears a striking resemblance to a spacecraft rather than a comet. Nevertheless, let us seriously consider the dark comet notion for a moment. Assume 3I 2023A3 is indeed outgassing, But the resulting gas is not producing the luminous coma we expect. How could this occur? It would require the gas to rapidly escape the surface with minimal entrained dust, and it would need to be transparent across visible wavelengths. Water vapor fits this description reasonably well. It is invisible and does not scatter light effectively. It only becomes apparent when it fluoresces under ultraviolet radiation or when dust particles mixed within it scatter sunlight. However, O, a breakdown product of water, does fluoresce. This is precisely what Crevier detected via radio signals. An emission from O should be observable in the ultraviolet and at specific optical wavelengths. If the coma contains 100 to the 33rd power O molecules, they should be emitting photons at a detectable rate. While perhaps not as bright as light scattered by dust, it should be measurable with sophisticated instruments. JUICE is equipped with such advanced instruments. The UVS spectrograph can detect O emissions. If O is present at the levels predicted by mass loss calculations, UVS will undoubtedly detect it. Conversely, if UVS fails to detect it, implying an O flux significantly lower than anticipated, then two possibilities emerge. Either the mass loss is not as substantial as calculated, meaning the acceleration is not a result of outgassing, or the water is not dissociating into O, which would be highly unusual and necessitate an explanation involving atypical chemistry or shielding from solar UV radiation. Another possibility suggests that the mass loss is real, but the ejected material is not water. Perhaps 3I 2023A3 is expelling substances that do not fluoresce, do not efficiently scatter light, and do not appear in spectral analyses. But what could such material be? Nitrogen, carbon monoxide, or noble gases, for instance. While these do not produce strong emission lines in the visible or ultraviolet spectrum, they also do not generate significant thrust. They are light elements. To achieve the same momentum transfer, they would need to be ejected at extremely high velocities, far exceeding the thermal speeds typically associated with sublimation. This brings us back to the notion of an active expulsion mechanism rather than passive evaporation. The absence of the expected mass cloud is the pivotal factor. If it is present, the natural explanation remains viable. If it is absent, the natural explanation collapses, leaving us to contemplate an interstellar object exhibiting behavior inconsistent with that of comets. Ground-based telescopes will have their opportunity to contribute starting in mid-November. By that time, 3I 2023A3 will have reappeared from behind the Sun, allowing observers worldwide to direct their instruments towards it, searching for the coma, measuring its brightness, and collecting spectral data. The International Asteroid Warning Network has already orchestrated a coordinated observation campaign. From November 27th to January 27th, numerous observatories will track 3I 2023A3, accumulating astrometric data to refine its orbit and photometric measurements to characterize its activity. This intensive observation period will span nearly 2 months. If the coma is present, and if the gas production rates align with the momentum requirements for the observed acceleration, this campaign will unequivocally document it. With multiple independent teams, diverse instruments, and observations across a wide range of wavelengths, the data will be unambiguous and free from controversy. The findings will be clear. Conversely, if the data reveals a faint coma, significantly smaller than predicted, with gas production rates that do not correlate with the momentum demands, then every observatory participating in this campaign will have contributed to one of the most profound discoveries in astronomical history: the confirmation that an interstellar object is capable of non-gravitational acceleration without the discernible mass loss that such acceleration should entail. December 19th marks a critical date. This is when the object will reach its closest approach to Earth, at a distance of 269 million kilometers. While this is a considerable distance by everyday standards, it is sufficiently close for the Hubble Space Telescope to resolve fine details. The James Webb Space Telescope will be able to collect high-resolution spectra. Ground-based telescopes will be able to measure positions with sub-arc-second precision. The geometric configuration for observation will be excellent, and the observing conditions will be optimal for this object. If 3I 2023A3 is indeed surrounded by a substantial gas cloud at this juncture, it will be readily observable. The cloud is expected to be even larger than it was at perihelion, as the gas will have had more time to expand. Although sublimation may have diminished as the object moved away from the Sun, the gas previously released will still be present, spreading outward and forming a coma potentially spanning hundreds of thousands or even millions of kilometers in diameter. Hubble's cameras would capture this with ease. The Webb and near-infrared spectrograph (NIR-SPEC) instruments could meticulously analyze its composition, identify the molecular species, quantify their abundances, and compare them to those found in solar system comets and to theoretical models of interstellar chemistry. However, if Hubble's images show a compact object, if Webb's spectra exhibit weak gas lines inconsistent with billions of tons of ejected material, and if the astrometric data confirms the continuation of non-gravitational acceleration post-perihelion without the corresponding mass loss, then we will possess definitive proof, not mere speculation or hypothesis. It will be proof that 3I 2023A3 is not behaving as a natural comet. The existence or non-existence of the missing mass cloud is the definitive factor. There is no middle ground. The underlying physics is exceptionally clear, and the predictions are highly specific. 5.5 billion tons is the calculated mass. Over the coming weeks, every major telescope within the solar system will be focused on this object, meticulously measuring it in an effort to confirm or refute the presence of this mass. 4 days remain until the JUICE mission, representing the initial test and the first genuine opportunity to ascertain the presence of the gas. If, however, JUICE returns images that do not depict the anticipated coma, then we must prepare ourselves for the subsequent developments. An object that accelerates without a visible exhaust plume is not adhering to the established principles we have spent centuries learning. It is engaging in some other behavior, something that requires our understanding and could represent either humanity's most significant discovery or its most unsettling existential question. The missing mass cloud. It will either be found, dispersed across millions of kilometers of space, faintly glowing under solar radiation, awaiting detection, or it will not. And if it is not, then everything changes. The current tally of anomalies stands at 9. The non-gravitational acceleration is anomaly number 9. It is not the first peculiarity, nor even the strangest, but it is the latest in a growing series of characteristics that distinguish 3I 2023A3 as unlike anything previously observed. When these anomalies are aggregated and their probabilities are multiplied, the cumulative odds become astonishing. 1 in 10 quadrillion is Lowe's estimation for the combined probability of all 9 anomalies occurring naturally within a single object. This is expressed as 1 in 10 to the 16th power, or 1 in 10 million billion when written out. These probabilities far surpass those associated with winning the lottery or even random cosmic occurrences. They are numbers so infinitesimal that they begin to challenge the notion that we are observing a mere collection of natural circumstances. Let us examine each of these 9 anomalies individually. Anomaly 1. Trajectory alignment with the ecliptic plane. The orbital plane of 3I 2023A3 is tilted by a mere 5 degrees relative to the ecliptic, the plane in which Earth and the other planets orbit the Sun. Most interstellar objects are expected to arrive from random directions, as the galaxy is 3-dimensional, with stars distributed throughout its disk and halo. An object ejected from a planetary system light years away should exhibit no particular alignment with the architecture of our solar system. The probability of arriving within 5 degrees of the ecliptic by chance is approximately 0.2%, or 1 in 500. Anomaly 2. The Sunward Jet. Between July and August 3I 2023, A3 displayed an anti-tail, a structure that pointed towards the Sun rather than away from it. Anti-tails can sometimes be optical illusions, perspective effects resulting from viewing a curved dust tail from a specific angle. However, detailed geometric analysis confirmed that this was not a perspective artifact. The structure was genuine and pointed sunward. Comets do not exhibit such behavior. The pressure exerted by solar radiation and the solar wind consistently pushes material away from the Sun. A sunward jet necessitates an alternative force, a mechanism that ejects material in a direction opposite to the expected outward flow. The scientific paper documenting this phenomenon concluded that it is inconsistent with known cometary behavior. Anomaly 3. Nucleus mass. 3I 2023. A3 possesses a nucleus of considerable size compared to other interstellar objects, measuring at least 5 kilometers in diameter, potentially larger. Mass estimates place it at 33 billion tons or more. This equates to approximately 1 million times the mass of 2I Oumuamua and 1,000 times the mass of 2P Borisov. Furthermore, it is traveling at a higher velocity than both of these objects. Kinetic energy is proportional to mass multiplied by velocity squared. A large, fast-moving object possesses immense energy, and the probability of detecting such an object so soon after commencing our search for interstellar visitors is exceedingly low, estimated at less than 0.1% according to population models. Anomaly 4. Water depletion. The gaseous plume detected by the James Webb Space Telescope and other observatories contained only 4% water by mass. In contrast, most solar system comets are composed of more than 50% water ice, with some exhibiting even higher percentages. Water is the most abundant volatile in the outer solar system due to its prevalence in molecular clouds, the stellar nurseries where stars and planets form. A comet with only 4% water is highly anomalous, suggesting either a vastly different formation environment or significant processing that led to water depletion. Anomaly 5. Extreme negative polarization. Polarization quantifies the orientation of light waves after scattering off a surface. Most objects exhibit positive polarization, meaning the reflected light waves tend to align perpendicular to the scattering plane. 3I 2023. A3, however, displayed extreme negative polarization, a phenomenon unprecedented among all known comets, including 2P Borisov. Based on comparisons with thousands of other measurements, the probability of this occurring naturally is less than 1%. While negative polarization can occur, extreme negative polarization is exceedingly rare and requires specific surface properties that most comets lack. Anomaly 6. The WOW signal correlation. In 1977, the Big Ear Radio Telescope in Ohio detected a powerful, narrowband signal emanating from the direction of the constellation Sagittarius. The signal persisted for 72 seconds, its intensity rising and falling in a pattern consistent with the telescope's beam pattern, and has never been detected again despite numerous follow-up attempts. This signal is known as the WOW signal, named after the exclamation written by astronomer Jerry Amon in the margin of the printout upon its discovery. The origin of the signal remains unknown. It could have been terrestrial interference, an astrophysical transient event, or something else entirely. When its trajectory is traced backward, 3I 2023 A3 originated from a direction within 9 degrees of the WOW signal's source, 9 degrees on the celestial sphere. The probability of an interstellar object arriving from within 9 degrees of any specific point is approximately 0.6%, or 1 in 167. While not impossible considering the vastness of the sky, this directional coincidence, when combined with all the other anomalies, forms another data point that does not align smoothly with the hypothesis of random arrival. Lowe has been cautious in overstating this connection, repeatedly clarifying that the WOW signal was almost certainly not directly from 3I 2023A3. The signal was detected 48 years ago, and 3I 2023A3 was significantly farther away at that time. If the object were transmitting radio waves with sufficient power to be detected across interstellar distances, we would have picked up the signal repeatedly by now from multiple telescopes. The absence of such detection suggests either it was not transmitting, it ceased transmitting, or the signal was a singular burst. Nevertheless, the directional coincidence is intriguing. If 3I 2023A3 originated from a planetary system in that region of the galaxy, and if that system harbored a technological civilization that dispatched both a radio beacon and a physical probe towards nearby stars, then arriving from the same direction would be logically consistent. This does not constitute proof, nor even strong evidence, but rather an interesting alignment that prompts questions worth investigating. Anomaly 7. L-band spectroscopy. Spectroscopic analysis performed in July and August revealed intense nickel emission lines within the coma. Nickel, the element with atomic number 28, not nickel compounds or alloys, but pure nickel vapor, was detected at a distance exceeding 4 astronomical units from the Sun. At this distance, temperatures should be far too low to permit metal sublimation. Furthermore, the abundance of nickel was high, significantly exceeding that of iron, which is typically about 20 times more abundant than nickel in cosmic material. 3I 2023A3 exhibited a strong nickel signature but very little iron. This inverted ratio is contrary to expectations. Comet experts have proposed that the nickel might be bound within volatile molecules, such as nickel tetracarbonyl, which sublimes at lower temperatures. However, this remains a speculative explanation, unconfirmed by direct observation, and necessitates unusual chemical processes that are not fully understood. Anomaly 8. Rapid brightening. Photometric data from stereo and GOES instruments documented a brightness increase that correlated with heliocentric distance raised to the power of -7.5. Comets from the Oort cloud typically exhibit exponents ranging between 2 and 4. Exponents exceeding 6 are exceptionally rare. The relevant scientific paper explicitly states that the reason for this rapid brightening remains unclear and significantly deviates from typical behavior. It is conceivable that the object possesses unusual volatile content, structural characteristics, or thermal properties. While possible, these explanations have not yet been substantiated, representing merely another anomaly requiring ad hoc explanations. Anomaly 9. Non-gravitational acceleration. 4 arcseconds of positional change indicate a measurable thrust, a momentum requiring billions of tons of ejected gas. We have already discussed this phenomenon in detail. It is a documented reality. It represents the culminating anomaly in this series, escalating the situation from mere interest to urgent concern. Now, let us consider the multiplication of probabilities, not as a literal calculation, as some of these anomalies may be interconnected. For instance, if the object possesses an unusual composition, this could potentially explain both the elevated nickel abundance and the depleted water content. Similarly, if it exhibits structural integrity, this could account for both its substantial mass and its ability to withstand the thermal stresses encountered during perihelion passage. A straightforward multiplication of independent probabilities is not appropriate if the events are not independent. However, even when accounting for potential correlations and applying generous estimations, the cumulative probability remains exceptionally small. Lowe's calculation yields a probability of less than 1 part in 10 to the 16th power, or 1 in 10 quadrillion. This represents the odds that all 9 of these distinct features would co-occur naturally within a single object originating from interstellar space. To provide perspective, there are approximately 100 billion stars within our galaxy. If every star were to expel a single interstellar object during its existence, and these objects were dispersed without preference, the likelihood of encountering one displaying all 9 anomalies associated with the 3 Atlas designation within our immediate vicinity would effectively approach 0. One would anticipate finding such an object across numerous galaxies rather than within our own solar system within 5 years of commencing our search for extraterrestrial travelers. Does this definitively establish 3 Atlas as an artificial construct? No. Probabilistic arguments do not constitute proof. Low probability occurrences are commonplace. Every specific permutation of coin flips is astronomically improbable when calculated beforehand, yet one such sequence is bound to manifest. Individuals achieve lottery victories despite seemingly insurmountable odds. Infrequent events are precisely that, rare, not impossible. However, probabilistic arguments do serve to guide our focus. When a concentration of low-probability events becomes apparent, when multiple independent anomalies converge within a single entity, this constitutes a signal. It may represent background noise or mere coincidence, but it warrants serious investigation rather than outright dismissal. The 9 anomalies are not concealed. They are publicly documented and accessible for verification. The raw data resides in archives, the analyses are published in scientific papers, and the reasoning is transparent. Should errors exist, other scientists are empowered to identify them, report them, and publish corrections. This is the fundamental mechanism of scientific progress. Assertions are rigorously examined, mistakes are identified, and flawed reasoning is exposed. To date, these anomalies have withstood scrutiny. Individual explanations have been proposed for some of them. Perhaps the alignment of its trajectory is purely coincidental. Perhaps the presence of nickel originates from tetracarbonyl. Perhaps its rapid brightening is attributable to a carbon dioxide-dominated composition transitioning to one dominated by water ice as temperatures escalate. Each anomaly, considered in isolation, can be rationalized through a combination of unusual, yet not impossible, circumstances. However, when all of them are considered collectively, the cumulative improbability becomes exceedingly difficult to disregard. Each purported explanation represents a unique scenario, with each anomaly necessitating the invocation of infrequent conditions. At a certain threshold, the accumulation of such rare conditions becomes less plausible than an alternative hypothesis, that these are not isolated coincidences, but interconnected attributes of an object whose true nature we have misinterpreted. A quantitative assessment scale, designated the Loeb scale, has been developed to evaluate this. This scale ranges from 0 to 10, where 0 signifies a definitively natural origin, and 10 indicates a definitively technological one. The scale integrates multiple lines of evidence, assigning weights based on their reliability and significance, and generates a score reflecting the degree to which the observations align with each hypothesis. 3 Atlas currently registers a score of 4 on this scale. This places it squarely between the natural and technological possibilities in an ambiguous and uncertain zone where neither hypothesis can be definitively ruled out based on the current data. Scores below 5 favor the natural hypothesis, while scores above 5 lend more credence to the technological one. A score of 4 signifies a critical juncture. 1 or 2 additional anomalies or more robust confirmation of existing ones could elevate this score. Conversely, the discovery of natural explanations that encompass multiple anomalies simultaneously could reduce it. The scale is not infallible, nor does it offer absolute proof. It serves as a framework for approaching the problem with quantitative rigor, moving beyond subjective intuition or rhetorical arguments. Presently, this framework indicates that certainty remains elusive. Further data is imperative. This brings us back to the months of November and December, the enigma of the missing mass cloud, the observations conducted after its closest approach to the Sun, and its proximate passage near Earth. Each piece of data we gather will either reinforce the natural explanation by demonstrating conventional causes for the anomalies, or support the alternative hypothesis by confirming the persistence and intensification of these anomalies under examination. The connection to the wow signal represents the most speculative anomaly in the ensemble. It is readily dismissible. A 9-degree segment of the sky encompasses a considerable area, housing thousands of stars. While the probability of any specific interstellar object originating from within this region is low, it is not infinitesimally small. Furthermore, we possess no definitive proof that the wow signal was of intelligent origin. It could have been a malfunction, interference, or an as-yet ununderstood natural astrophysical phenomenon. Nevertheless, it persists in consideration because the wow signal was unique. Across 50 years of SETI observations, encompassing millions of stars and billions of detected signals, nothing else has exhibited its characteristics. Specifically, it possessed a unique combination of narrow bandwidth, high intensity, and a celestial origin consistent with an extraterrestrial source. The vast majority of SETI detections are quickly identified as artificial, such as satellites, radar signals, or terrestrial broadcasts. The wow signal defied such categorization and remains unidentified. If 3 Atlas is indeed natural, then its directional correlation is rendered insignificant, a mere coincidence. It could have originated from any number of possible directions, and it happened to emanate from the same sector of the sky where an unusual observation was previously made. So what? The universe is vast, and coincidences occur. However, if 3 Atlas is not natural, then this correlation becomes compelling. Not definitive proof, but intriguing nonetheless. It suggests the possibility, however remote, that the wow signal and the object are connected. Perhaps the signal served as a beacon, part of a network, or something entirely different, but originating from the same source. Alternatively, it might be that the object is artificial, but entirely unrelated to the wow signal. These are distinct questions. Radio telescopes are currently monitoring 3 Atlas. Avi Loeb has confirmed in his blog post that observers have been requested to search for transmissions. If the object is emitting at radio wavelengths, we will detect it. The sensitivity of modern radio telescope arrays is exceptional. Any signal, even a faint one, will be discernible. And should we detect such a signal, should 3 Atlas suddenly commence transmitting in radio frequencies with patterns unequivocally distinct from natural emissions, then the cumulative stack of anomalies becomes secondary. At that point, we will possess direct evidence. All other inquiries will then become subordinate to the immediate reality of receiving a message from a technological artifact not of human origin. However, this remains speculative, a product of wishful thinking. A more probable scenario involves silence. No radio signals, no laser emissions, no unambiguous technological signatures. Merely the 9 anomalies continuing to accumulate, awaiting explanations that do not necessitate invoking extraordinary circumstances for each individual feature. The data will ultimately provide the resolution. On November 4th, observations from the JUICE mission are scheduled. Mid-November will bring observations from ground-based telescopes. December 19th is slated for observations by the Hubble and Webb telescopes. Each subsequent round of observations will either validate the anomalies or resolve them. Each measurement will either increase or decrease the score on the Loeb scale. Currently, we stand at a score of 4, signifying ambiguity and uncertainty. the most candid assessment given our current knowledge. In a few weeks, we will possess more information, potentially a substantial amount more. The aggregation of anomalies is a tangible phenomenon, and their cumulative probability has been calculated. The fundamental question is no longer whether 3 Atlas is unusual. It is whether unusual signifies an unprecedented natural phenomenon or something else entirely, something we have sought in various forms for as long as we have contemplated our solitude in the cosmos. December 19th marks a significant date, 51 days post-perihelion, when 3 Atlas will be approximately 269 million kilometers from Earth. This distance is roughly equivalent to 1.8 astronomical units, or approximately the separation between Earth and Mars when they occupy opposite points in their respective orbits. While considerable by terrestrial standards, it is close enough for every major telescope, both terrestrial and orbital, to obtain clear observations. 6 days prior to Christmas, Avi Loeb deliberately posed the question, will 3 Atlas dispatch numerous probes toward Earth as Christmas gifts for humanity? He is not predicting this eventuality nor claiming its high probability. Instead, he is raising the possibility of a scenario that becomes plausible if the object is not natural, if its perihelion passage represented a maneuverable opportunity, and if its trajectory was intentionally designed rather than random. The physics governing small probes is straightforward. If 3 Atlas functions as a mothership carrying smaller vehicles or instruments, the optimal moment for their release would be during perihelion. The immense gravitational pull of the Sun provides substantial energy. A modest velocity change applied at perihelion can result in a significant trajectory alteration at a later point. Probes can be directed towards various planets and destinations throughout the solar system, utilizing the Sun's gravity to bend their paths into desired configurations. Earth, with its detectable biosignatures, oxygen in the atmosphere, surface water, the spectral signature of chlorophyll in reflected light, and radio emissions from our technological civilization, stands out as a prime target for investigation. A probe launched from 3 Atlas toward Earth during perihelion would not necessitate substantial thrust. The object's perihelion distance was 1.36 astronomical units, while Earth's orbit is at 1 astronomical unit. The difference is minimal. A velocity alteration of only a few hundred meters per second could shift a probe's trajectory from following 3 Atlas's hyperbolic path to intersecting Earth's orbital path at a subsequent time. 51 days after perihelion, on December 19th, a small probe, traveling at an average velocity of tens of kilometers per second, could traverse the distance from 3 Atlas's perihelion location to Earth. This would not be a comfortable journey, nor would it afford a significant margin for error, but it is a feasible trajectory. The timing aligns. Loeb is not asserting that this will occur. He is suggesting it is a scenario warranting careful observation. The Galileo project operates 3 observatories located in Harvard, Colorado, and California, each equipped with cameras and sensors designed to detect anomalous objects within Earth's atmosphere and near-Earth space. These instruments are calibrated, automated, and operate continuously, collecting data and flagging any entity that deviates from the expected patterns of known aircraft, satellites, meteors, or astronomical objects. Should multiple probes arrive in December, entering Earth's vicinity and exhibiting discernible activity, such as maneuvering or transmitting, the Galileo observatories might detect them. This is the overarching concept. Not to survey the entire celestial sphere, an impossible task for 3 ground-based stations, but to systematically monitor and anticipate the potential detection of any unusual occurrences within their observational fields. The close approach on December 19th holds significance for additional reasons. This date represents the most opportune moment for ground-based telescopes to observe 3 Atlas in detail. While the object will be receding from the Sun along its hyperbolic trajectory, it will remain sufficiently close to Earth for large aperture telescopes to resolve structural features, measure photometry, and collect spectra with a high signal-to-noise ratio. The Hubble Space Telescope is scheduled for observations. The Space Telescope Science Institute has already allocated observation time. Hubble's cameras possess the resolution necessary to image 3 Atlas with sufficient clarity to discern its nucleus, measure the size of its coma, and detect any signs of fragmentation or asymmetry. The Wide-Field Camera 3 can capture spectra across a range from ultraviolet to near-infrared, encompassing wavelengths where gas emission lines appear, where dust scattering is dominant, and where the comet's color and composition are revealed. The James Webb Space Telescope will also conduct observations. With its substantial 6.5-meter mirror and exceptional infrared sensitivity, Webb can penetrate dust clouds that pose challenges for optical telescopes. Webb's near-infrared spectrograph, NIR-SPEC, can analyze the molecular composition of the coma, identifying individual species, quantifying their abundances, and comparing these ratios to those of solar system comets and to theoretical predictions for interstellar chemistry. Any anomaly in the gas composition, anything inconsistent with standard cometary makeup, will be detected by NIR-SPEC. Ground-based telescopes worldwide will participate in this observational campaign. The International Asteroid Warning Network, IAWN, has coordinated a campaign running from November 27th through January 27th, encompassing the December 19th close approach. Dozens of observatories, both professional and amateur, equipped with instruments ranging from small backyard telescopes to massive 10-meter giants like Keck and the Very Large Telescope, will track 3 Atlas, precisely measure its position, record its brightness, and gather as much data as possible. This initiative serves as planetary defense training. IAWN treats every close-approaching object as an exercise, providing an opportunity to practice the coordination and communication protocols that would be essential if a genuine threat were identified. 3 Atlas poses no immediate threat. Its trajectory does not intersect Earth's orbit. However, it represents a valuable opportunity. This rare interstellar visitor, observable for an extended period, provides a crucial test case for assessing the global astronomical community's response to anomalous celestial objects. The astrometric data will be of paramount importance. Precise positional measurements acquired from multiple observatories over numerous nights will enable NASA's Jet Propulsion Laboratory, JPL, to refine the object's orbit with extreme accuracy. Any deviations from a purely gravitational path will become readily apparent. If 3 Atlas exhibited propulsive maneuvers post-perihelion, or if non-gravitational accelerations continued or altered direction, the astrometry would reveal these changes. Trajectory alterations are virtually impossible to conceal when hundreds of precise measurements are distributed across several weeks. Furthermore, if the trajectory indicates sustained acceleration, continuous thrust, or deviations correlating with specific events or times, this would constitute evidence of active control, suggesting something is actively adjusting its path rather than passively responding to solar heating. While natural outgassing can generate thrust, it is typically erratic, variable, and dependent on localized conditions on the nucleus's surface. Controlled thrust, conversely, is characterized by smoothness, predictability, and a directed vector. Astrometric data will be instrumental in distinguishing between these two scenarios. December 19th also represents a peak period for brightness measurements. If 3 Atlas is a comet that shed billions of tons of mass at perihelion, its brightness should be declining rapidly as it moves away from the Sun. The rate of sublimation diminishes with increasing distance. The coma disperses, and the dust settles. Active comets typically fade after perihelion, sometimes dramatically, as the energetic processes driving their activity decrease. However, if the brightness plateaus, remains higher than predicted, or fades more slowly than models anticipate, this would be anomalous. Such behavior would be consistent with an internal light source, something generating illumination independent of solar heating. This internal light source would not necessarily be intense, but merely sufficient to offset the expected decline and maintain a brightness level exceeding that of a passively reflective object. Chronographic data already indicated a blue-shifted light emission rather than purely reflected light. If this observation continues post-perihelion, and if Webb, Hubble, and ground-based spectrographs detect gas emission lines at intensities not correlated with distance from the Sun, this would bolster the hypothesis of activity driven by a source other than solar flux. Conversely, if 3 Atlas fades rapidly, its coma dissipates, and its spectra exhibit declining gas production consistent with cooling as the object recedes, this would support the natural comet hypothesis. Comets eventually exhaust their supply of volatile materials near their surface. The remaining ice becomes buried beneath a layer of dust and refractory material, leading to a cessation of activity. The object then transforms into an inert, rocky mass drifting through space. The outcome will be clarified by the end of December. The observational schedules are set, and the data will be acquired. Once obtained, the debate will shift from speculation to evidence-based analysis. Loeb's comment about Christmas gifts is provocative. It is designed to stimulate contemplation of the full spectrum of possibilities. If 3 Atlas is indeed a mothership and released probes at perihelion, where might those probes have traveled? What actions might they have taken? How would we have detected them? The simple truth is that we do not know. We have no prior experience with alien technology and thus no empirical basis for predicting its appearance, behavior, or the signatures it might produce. We can only extrapolate from fundamental principles, from physics, and from the constraints that govern all material objects, irrespective of their origin. A probe maneuvering in space requires propulsion. Propulsion necessitates energy and either reaction mass or an equivalent mechanism, such as solar sails utilizing photon pressure. If the probe is small, measuring a few meters or less, it might be difficult to detect optically unless it is in very close proximity. However, if it is actively maneuvering, changing its velocity, it could generate exhaust, heat, or electromagnetic emissions, phenomena that telescopes and radar systems could potentially detect if they are positioned and oriented correctly at the opportune moment. The Galileo project is not the sole entity engaged in monitoring. The Space Surveillance Network operated by the U.S. Space Force tracks objects within Earth orbit and near-Earth space, cataloging satellites, debris, and any object sufficiently large to pose a collision risk. Should a small probe enter cislunar space, the region between Earth and the Moon, the Space Surveillance Network might detect it contingent upon its size, reflectivity, and trajectory. However, detection does not equate to identification. Small objects are routinely detected. The majority are identified as space junk, fragments of defunct satellites, spent rocket stages, or debris resulting from collisions. Distinguishing between a natural meteoroid, a piece of human-made debris, and a hypothetical alien probe necessitates a detailed analysis of its trajectory, light curve, and radar return characteristics. If an unusual object is detected in December, one that does not conform to the established catalog, it will undoubtedly attract attention and be subjected to tracking. Should it exhibit controlled motion, maneuvering in ways that preclude natural or human origins, then we will have our answer. At that point, the Christmas question will be resolved in the most dramatic manner conceivable. However, this represents a less probable scenario, one requiring 3 Atlas not only to be unusual, but also to be actively engaged in exploration. A more likely outcome is that December 19th will pass without incident. Hubble and Webb will collect their data, ground-based telescopes will record positions and brightness measurements, and 3 Atlas will continue its trajectory, behaving as comets typically do, offering no clear evidence of anything beyond natural phenomena. This would be the anticipated outcome, the unremarkable conclusion, affirming our current understanding of interstellar objects and allowing for a collective sense of relief, secure in the knowledge that the universe is predominantly composed of rocks and ice, rather than spacecraft and probes. Regardless of whether the outcome is deemed boring or expected, the observations will proceed. The data will be collected. By the end of December, around Christmas, we will have answers. Not exhaustive answers, nor definitive proof one way or the other, but sufficient data to shift the probabilities, to update the Loeb scale score based on empirical measurements rather than speculation. December 19th, 51 days after perihelion, marks the closest approach, the moment when Earth has its most optimal vantage point to observe the third recorded interstellar visitor, and perhaps, just perhaps, the moment we discover if we have been observing a visitor in more than one sense of the term. The fundamental Christmas question is not whether 3 Atlas will deliver gifts. Rather, it is whether we are prepared for whatever answer the data ultimately provides. Are we prepared to accept the evidence, even if it contradicts our preconceptions? Are we willing to follow the evidence rather than adhere to our pre-existing biases? Avi Loeb believes we are. This conviction drives his persistent questioning, his publication of papers that challenge conventional thought, and his proposal of scenarios that elicit discomfort among his colleagues. He holds that science flourishes best when it is fearless, when it confronts the universe unflinchingly, and when it acknowledges the possibility that nature might be more extraordinary than we imagine. Brian Cox advocates for caution. This is why he pushes back, labels speculation as drill, likely a typo for drivel or a similar term implying nonsense, and emphasizes natural explanations. He believes science functions most effectively when it is disciplined, demanding robust evidence before embracing extraordinary claims and protecting the public from false hope and misleading narratives. Both individuals are dedicated to the pursuit of truth. Both parties are aiming to unravel the mystery of 3I Atlas, but they differ on the methodology. The 19th of December is set to be the decisive date, challenging both approaches. The forthcoming data will either validate a cautious stance by revealing prosaic explanations for the observed anomalies, or it will endorse a proactive approach by demonstrating that these anomalies persist and intensify. Regardless of the outcome, we will proceed with augmented understanding, reduced uncertainty, and a clearer perspective. 50 days remain, that is all. 50 days until the closest encounter. 50 days until the collective gaze of our telescopes is fixed upon 3I Atlas, meticulously gathering every available photon. 50 days until we ascertain whether the Christmas question is merely a rhetorical flourish or a genuine possibility demanding serious consideration. Meanwhile, as we await these revelations, 3I Atlas continues its relentless outward journey, receding from the Sun at a velocity of 61 kilometers per second. It carries its enigmatic cargo, whatever its true nature may be, toward Jupiter's orbit and beyond. This celestial traveler remains indifferent to our discussions, our queries, proceeding on its millennia-old trajectory through the vast emptiness between the stars. Chapter 8. The Political Undercurrent. There exists a photograph, unseen by the public, a high-definition image of 3I Atlas captured by the most advanced camera ever dispatched to Mars. This image was taken at the precise moment the interstellar visitor traversed within 29 million kilometers of the red planet. The sophisticated camera aboard NASA's Mars Reconnaissance Orbiter achieved a resolution of 30 kilometers per pixel, meaning that a single picture held the potential to resolve some of the most fervent debates surrounding the object's true composition. This photograph is a reality. It was recorded on the 2nd of October, 2025. As of the 31st of October, 2025, it remains inaccessible, withheld from both the scientific community and the public. The impediment? A governmental shutdown that commenced on the 1st of October. On that very day, coincident with 3I Atlas's closest approach to Mars, the United States federal government experienced a lapse in funding. NASA, along with numerous other federal agencies, entered what is officially termed a lapse in appropriations. Non-essential personnel were instructed to remain at home, and the dissemination of data was suspended. Consequently, the team responsible for the high-resolution imaging, despite having successfully acquired what could be the most significant astronomical photograph of the decade, found themselves unable to share their groundbreaking work with the world. This situation should not transpire. Scientific endeavors, particularly time-sensitive observations of celestial bodies that will never reappear, ought not to be held hostage by political gridlock. Yet, we find ourselves witnessing a scenario where partisan budget disputes in Washington prevent astronomers from accessing data that could furnish answers to fundamental questions about an interstellar visitor. The irony is almost too profound to bear. We possess the image. The spacecraft performed its duty flawlessly. The camera functioned perfectly. However, a capricious twist of American politics renders this invaluable data effectively non-existent. Avi Loeb, never one to remain silent when he perceives science to be compromised, has been outspoken regarding this predicament. He deems it unconscionable that critical observational data could be withheld during such a fleeting window of opportunity. 3I Atlas will not return. This is our sole chance for close-up study. And while Congress deliberates over spending legislation and shutdown deadlines, the object continues its trajectory, drifting ever farther from Earth, diminishing in brightness, becoming more elusive to observation, and gradually receding into the cosmic darkness from which it emerged. Enter Congresswoman Anna Paulina Luna. The representative from Florida's 13th Congressional District has unexpectedly emerged as a staunch advocate for transparency in the 3I Atlas investigation. Loeb engaged directly with her, briefing her on the object's anomalies and the pressing need for the high-resolution imagery. In response, Luna dispatched a formal letter to Sean Duffy, NASA's acting administrator, imploring the agency to release the images without delay and to explore the feasibility of utilizing the Juno spacecraft, currently near Jupiter, to observe 3I Atlas during its flyby in March of 2026. Luna's involvement is noteworthy as it represents a rare instance of a congressional member taking a direct interest in astronomical research, particularly research that touches upon questions concerning extraterrestrial technology. Her correspondence acknowledged the significance of the data and urged NASA to prioritize its release, notwithstanding the administrative complexities arising from the shutdown. This action served as a clear signal, indicating that at least some elected officials recognize the gravity of the situation. However, Luna's efforts also underscore a more pervasive issue: the necessity for congressional intervention to release routine scientific data reveals the inherent fragility of our systems. We tend to envision space exploration as an enterprise transcending political divides, a pure pursuit of knowledge beyond partisan disputes. Yet the reality is that every undertaking by NASA is contingent upon federal funding, federal employees, and federal bureaucracy. When this framework falters, even for a brief period, the repercussions reverberate throughout the entire endeavor. The timing of the shutdown could scarcely have been worse. October 1st marked not just another date, but the commencement of the fiscal year, the critical juncture at which government funding requires renewal to ensure continued operations. Congress had months to approve a budget, They were aware of the impending deadline. Nevertheless, as has become depressingly commonplace in American politics, they failed to reach a consensus in time. The government entered a shutdown, and consequently, the flow of scientific data came to a standstill. NASA personnel responsible for managing the high-resolution camera, processing raw images, and preparing them for public dissemination were furloughed. They were instructed to await further instructions until Congress resolved the funding impasse. This is standard protocol during shutdowns. Non-essential functions cease, with only mission-critical operations continuing. However, the question that seems to elude a satisfactory answer is this: how is the release of data pertaining to an interstellar object not considered mission-critical? 3I Atlas represents an unparalleled scientific opportunity. It is merely the third confirmed interstellar visitor humanity has ever detected. It exhibits numerous anomalies that challenge our current understanding of cometary behavior, and it is present in our solar system at a time when we have spacecraft strategically positioned for observation. If ever there was a moment to prioritize the swift release of data, this is it. Yet, the bureaucratic machinery of government operates according to its own inherent logic, seemingly oblivious to astronomical urgency. Loeb has been careful to avoid attributing the delay to malice or conspiracy. He does not believe NASA is deliberately withholding the high-resolution images because they contain startling or inexplicable revelations. His assessment is simpler and, in some respects, more exasperating. It is incompetence, not conspiracy. Bureaucratic inertia, not a cover-up. The system is flawed not because individuals are attempting to conceal the truth, but because the system itself is ill-equipped to manage such situations. However, this distinction, while significant, does little to mitigate the sheer infuriation of the circumstances. Whether the delay stems from conspiracy or incompetence, the consequence remains the same. Scientists are denied access to crucial data. The public is deprived of images that could resolve ongoing debates, and each passing day renders future observations progressively more challenging. As 3I Atlas recedes into the cosmic expanse, the high-resolution image holds particular importance due to its potential to illuminate the object's structural characteristics. With a resolution of 30 kilometers per pixel, we could potentially discern whether 3I Atlas is a singular, cohesive entity or a collection of smaller fragments bound by weak gravitational forces. We might be able to precisely measure the brightness of individual pixels, thereby refining our estimates of the object's surface area and albedo. We could investigate asymmetries in the coma, detect subtle signs of jetting activity, or identify evidence of rotation or tumbling. All of this information is vital. It is crucial for determining whether 3I Atlas is a natural comet, as most scientists presume, or something far more extraordinary. It is essential for comprehending the formation and evolution of interstellar objects, and it is indispensable for planning subsequent observations, not only of this specific object, but also of others that will inevitably follow. The Vera C. Rubin Observatory in Chile is anticipated to detect new interstellar visitors on a monthly basis once it achieves full operational status. Each discovery will present a fleeting opportunity. We must develop improved protocols for rapid data dissemination, enhance coordination among agencies, and better shield time-sensitive scientific endeavors from political disruptions. Loeb's proposed remedy is straightforward. Establish explicit protocols that designate specific categories of astronomical observations as high priority, mandating their expedited release irrespective of governmental shutdowns or budgetary crises. It should become established policy that data pertaining to interstellar objects is shared promptly within hours or days of acquisition, rather than weeks or months later, following protracted bureaucratic review. These events should be treated as the rare and precious opportunities they are, moments to study visitors from beyond our solar system. Would such a policy resolve all issues? No. There will always be valid justifications for delays, such as equipment malfunctions, data corruption, or the necessity for calibration and validation. Science cannot be unduly accelerated without compromising its integrity. However, there exists a substantial disparity between meticulous scientific scrutiny and administrative paralysis. Currently, we are experiencing the latter, which is unacceptable. The political dimension of 3I Atlas extends beyond the specific case of the high-resolution imagery. Broader questions arise concerning how we approach discoveries that might have implications for extraterrestrial intelligence. If an object were definitively identified as technological rather than natural, how would that information be disseminated? Who would be responsible for making such an announcement? Are there any protocols in place, however informal, for managing public communication regarding such a revelation? The answer is unsettling. There are no formal protocols. The SETI community adheres to a set of guidelines, originally formulated in the 1980s and periodically updated, outlining how researchers should handle potential detections of extraterrestrial signals. However, these guidelines are voluntary, not legally binding, and they do not specifically address the scenario of discovering alien technology within our solar system. To put it plainly, we are improvising as we go. This lack of preparedness creates fertile ground for confusion, miscommunication, and potentially widespread panic. Should NASA or another space agency uncover evidence of extraterrestrial technology, they would face immense pressure to release that information immediately, while simultaneously needing to rigorously verify their findings before making any public pronouncements. The inherent tension between transparency and accuracy would be colossal. In the current political climate, characterized by diminished public trust in institutions and the rapid proliferation of conspiracy theories online, managing such an announcement would prove exceptionally challenging. The 3I Atlas situation, even absent any confirmed evidence of technology, offers a glimpse into these impending difficulties. Loeb's public statements concerning the object's anomalies have garnered considerable media attention and public interest. Some individuals are invigorated by the prospect of observing alien technology, while others remain skeptical, viewing Loeb as an attention seeker or a sensationalist. The scientific community itself is divided, with some researchers supporting Loeb's call for comprehensive investigation, while others dismiss his concerns as exaggerated. Introducing a government shutdown and delayed data releases into this complex environment creates a perfect storm for speculation and distrust. If NASA appears to be withholding information, even for mundane bureaucratic reasons, it fuels narratives of cover-ups and concealed knowledge. The longer the delay persists, the more individuals will question what NASA might be concealing. While the explanation is likely mundane, simple governmental inefficiency, the perception of secrecy inflicts genuine damage on public confidence. Luna's intervention offers some measure of assistance. Her willingness to publicly advocate for data release signifies political oversight and a commitment from elected officials to demand transparency. However, it also highlights the extent to which scientific progress has become reliant on individual champions within the government. What happens if Luna shifts her focus to other matters? What if future interstellar visitors arrive during periods when no member of Congress expresses particular interest in astronomy? Will we simply accept that critical data might remain unexamined? The underlying structural problem extends beyond any single shutdown or any isolated object. We have constructed a scientific infrastructure heavily dependent on federal funding and federal institutions, rendering it susceptible to political disruptions. While private entities and international collaborations can help bridge certain gaps, they cannot replicate the scale and coordination provided by governmental agencies. SpaceX can launch telescopes, but it cannot mandate data sharing across multiple observatories. The European Space Agency can fund missions, but it cannot compel NASA to expedite information releases. Consequently, we are left with an uncomfortable truth. The most significant astronomical discovery of the decade might currently reside on a hard drive at the University of Arizona, the location of the High-Resolution Imaging Operations Center, inaccessible due to Congress's failure to pass a budget on time. Even when the shutdown eventually concludes, as it inevitably will, there is no guarantee that the lessons learned will translate into preventing similar disruptions in future shutdowns. Loeb contends that this situation necessitates change, advocating for systemic reforms not only for 3I Atlas, but for all future interstellar visitors. He argues that scientific data concerning objects originating from beyond our solar system should be accorded exceptional urgency and shielded from typical bureaucratic delays. Is he correct? Almost certainly. Will anything tangible change? That remains to be seen. The political dimension of 3I Atlas is less glamorous than its scientific enigmas. It involves no complex equations to solve or observations to analyze, merely the grinding frustration of navigating dysfunctional institutions. Yet, its importance is equal, for sophisticated telescopes and brilliant scientists are rendered impotent if the data they generate cannot be shared in a timely manner. And if we cannot effectively manage this situation for 3I Atlas, what hope do we possess for handling subsequent interstellar visitors, or indeed, the first genuine signal from an alien civilization? These are not hypothetical concerns. Interstellar objects are regularly traversing our solar system. We have only recently begun detecting them because our telescopes previously lacked the necessary sensitivity. However, as our observational capabilities advance, we will detect more, many more. The Vera C. Rubin Observatory alone is projected to discover dozens per year. Each will present a limited window of opportunity, measured in weeks or months. If our systems cannot adapt, if we remain paralyzed by political dysfunction and bureaucratic inertia, we will squander these opportunities. We will watch helplessly as visitors from distant star systems slip past us, unexamined, their secrets preserved solely because of our disorganization. The high-resolution image will eventually be released. The shutdown will cease, funding will be restored, and the data will become accessible. However, the delay itself constitutes a failure, a preventable failure that underscores systemic weaknesses we can no longer afford to disregard. 3I Atlas is imparting numerous lessons. Some pertain to astrophysics and cometary behavior. However, one of the most significant lessons has no bearing on science whatsoever. It concerns politics, bureaucracy, and the fragile infrastructure that underpins scientific discovery. And it is a lesson we urgently need to internalize. Chapter 9. Juno's Final Opportunity. A spacecraft currently orbiting Jupiter was never intended to become part of the 3I Atlas narrative. Juno was launched from Cape Canaveral in August of 2011 with a clearly defined mission to study Jupiter's composition, map its gravitational and magnetic fields, and probe the mysteries of the solar system's largest planet. For over a decade, Juno has diligently pursued this objective. Orbiting in a highly elliptical path, it swoops close to Jupiter's cloud tops before retreating to safer distances, amassing data that has profoundly reshaped our understanding of gas giants. Juno's mission was slated to conclude in September of 2025. The plan was straightforward. Following years of productive scientific work, the spacecraft would be intentionally guided into Jupiter's atmosphere, burning up to prevent any potential contamination of Europa or other moons that might harbor life. A noble end for a spacecraft that had served humanity commendably. However, the discovery of 3I Atlas presented Juno with an unforeseen opportunity. On March 16, 2026, 3I Atlas will pass within 53.6 million kilometers of Jupiter. This is considered a close proximity in astronomical terms. It is close enough that a spacecraft already orbiting Jupiter could potentially be redirected to intercept the interstellar visitor's trajectory. Avi Loeb, collaborating with Adam Hibbert and Adam C., is meticulously calculating the precise maneuvers required. The numerical challenges are formidable, yet not insurmountable. Juno would need to execute what is known as a Jupiter-Obath maneuver. This entails two meticulously timed engine firings. The first, scheduled for September 9, 2025, would lower Juno's perihelion, the point of closest approach to Jupiter, 8 days prior to the spacecraft's original planned plunge. The second burn would occur at this adjusted perihelion, leveraging Jupiter's immense gravitational pull to slingshot Juno onto an intercept course with 3I Atlas. The total delta V, the requisite change in velocity, is 2.6755 kilometers per second. This represents a significant demand on Juno's fuel reserves. The spacecraft has been operational for over 14 years, and its main engine has not been utilized since 2016, when concerns regarding the tank pressurization system prompted NASA to cancel planned maneuvers. Attempting to ignite it now carries considerable risk. The engine might fail to operate, or worse, it could experience a catastrophic malfunction, terminating the mission prematurely. But if successful, if the engine fires as intended and Juno can reach 3I Atlas, the scientific rewards would be extraordinary. A close flyby, potentially within 27 million kilometers, with instruments designed for planetary science reoriented toward an interstellar visitor. No telescope on Earth or in Earth orbit could rival such proximity, not even remotely. What might Juno discern? What data could it gather that ground-based observatories cannot? Let us begin with the fundamental instruments. Juno is equipped with a visible light camera designated JunoCam. This instrument was primarily included for public engagement purposes, enabling the public to witness Jupiter's swirling cloudscapes in exquisite detail. However, JunoCam could photograph 3I Atlas from a distance measured in tens of millions of kilometers, rather than hundreds of millions. This translates to enhanced resolution, clearer detail, and the capacity to discern structural elements and features imperceptible from Earth. Furthermore, Juno possesses the Juno Infrared Spectrometer, GIRAM. This instrument maps temperature and composition by analyzing the infrared light emitted or reflected by celestial objects. When applied to 3I Atlas, GIRAM could detect thermal signatures emanating from the nucleus, map the distribution of volatile compounds within the coma, and identify specific molecules that are challenging or impossible to observe from Earth. If the object is being heated by internal processes, rather than solely by solar radiation, GIRAM might be capable of identifying such an anomaly. Juno's magnetometer, designed to study Jupiter's powerful magnetic field, could potentially detect any magnetic signature originating from 3I Atlas. Natural comets do not possess inherent magnetic fields. They are essentially chunks of ice and rock that are magnetically inert. However, if 3I Atlas were in some way artificial, if it contained metallic components or operational electrical systems, a detectable magnetic anomaly might be present. However improbable, the magnetometer possesses the sensitivity to detect such subtle variations. The microwave radiometer, or MWR, penetrates the subsurface by analyzing thermal emissions across a spectrum of wavelengths. For Jupiter, this capability allows scientists to peer through its dense cloud layers and chart temperature profiles at various depths. In the case of 3I Atlas, the MWR could potentially discern between a solid core and a loosely aggregated mass, or differentiate between compact material and loosely bound debris. This would offer insights into its internal composition, information unattainable by conventional optical telescopes. Juno's gravity science instrument by meticulously tracking the spacecraft's velocity, measures gravitational fields. This function was paramount in understanding Jupiter's internal mass distribution. Applied to 3I Atlas, even a distant flyby could establish parameters for the object's total mass. If the gravity measurement indicates a mass inconsistent with its observed size and activity, the implications would be profound indeed. The energetic particle detector and the radio and plasma wave sensor are designed to identify any anomalous particle emissions or electromagnetic signals. Should 3I Atlas be outgassing in a typical manner, these instruments would register the characteristic signature of ionized particles interacting with the solar wind. Conversely, any artificial radio transmissions, however faint, might be detectable by Juno. While the likelihood is slim, the instruments are poised to listen. Finally, Juno's ultraviolet spectrograph offers the capacity to analyze the atmospheric composition around 3I Atlas with a precision far exceeding Earth-based observations. UV spectroscopy elucidates details regarding molecular structures, their relative abundances, and temperatures. It could either confirm or invalidate claims about its water content, identify trace elements, and provide a comprehensive chemical inventory of the ejected material. All this data, gathered from millions of kilometers closer than any terrestrial observatory, would constitute the most thorough examination of an interstellar object ever undertaken. This endeavor would not necessitate the construction of a new spacecraft or the initiation of a dedicated mission. It would simply require NASA's approval of the maneuver, confirmation of Juno's engine functionality, and the execution of the necessary propulsion burns with the agency's renowned precision. So, why has this opportunity not been pursued? The impediments are a blend of technical and political challenges. On the technical front, there exists genuine uncertainty regarding the continued operability of Juno's propulsion system. The primary engine was engineered for deep space maneuvers during the cruise phase and for Jupiter orbit insertion. Subsequently, it was intended for periodic use to fine-tune Juno's orbit. However, pressurization issues encountered in 2016 compelled mission planners to forego these adjustments. The spacecraft has since maintained its original science orbit, employing its smaller reaction control thrusters for attitude adjustments, leaving the main engine disengaged. Can an engine that has remained inactive for 9 years still function? The answer is uncertain. Engineers have analyzed telemetry data and believe there is a reasonable probability of success, but reasonable falls short of definitive assurance. Should the engine fail to ignite, or worse, experience a catastrophic failure, Juno would be lost. Not at the conclusion of its successful mission after years of valuable science, but in a high-stakes attempt to intercept an interstellar comet. Such an outcome would reflect poorly. It would invite criticism from those advocating for NASA to adhere to its core objectives rather than chase speculative possibilities. From a political standpoint, extending Juno's mission necessitates financial resources. The spacecraft's operational life was projected to conclude in September 2025, aligning with the expiration of its approved budget. Congressional appropriations operate on fixed schedules. Missions receive funding for defined periods, and such funding ceases upon their expiry, thereby terminating the mission. Extending Juno's operations beyond September 2025 would require supplementary funding, enhanced oversight, and additional justification to Congress. This is where Anna-Paulina Luna's correspondence becomes pertinent once more. By formally recommending that NASA evaluate the utilization of Juno for observing 3I Atlas, Luna provided a political justification for an extended mission. She offered NASA a rationale for requesting additional funds, a justification extending beyond merely prolonging a successful mission's lifespan. However, correspondence from Congress does not equate to budgetary allocations. Such letters signal support, but do not automatically translate into allocated funds. Furthermore, there is the question of mission prioritization. NASA manages numerous spacecraft throughout the solar system and beyond. Every dollar allocated to extending Juno represents a dollar not available for other projects. These could include other missions, different scientific priorities, or other researchers with equally compelling needs for resources. The agency must balance competing demands, distribute finite funds, and justify each decision to oversight committees. Diverting Juno towards 3I Atlas signifies foregoing other potential undertakings. This calculation is not straightforward. A.V. Loeb, unsurprisingly, considers the decision self-evident. The scientific benefits of a Juno flyby demonstrably outweigh the associated risks and expenditures. Interstellar objects are infrequent occurrences. 3I Atlas may be 7 billion years old, a pristine relic from the Milky Way's thick disk, offering insights into galactic evolution unattainable through other means. Juno is already in position, operational, and its costs have been incurred. Utilizing it to study 3I Atlas is not a new mission, but an opportunistic extension of an existing one. The required delta V falls within the spacecraft's theoretical capabilities. The observation window is clearly defined. Everything appears to align. However, Loeb is a scientist, not an administrator. He can champion the flyby, perform trajectory calculations, engage with Congress, and generate public enthusiasm. What he cannot do is make NASA's decisions for them. That authority rests with the agency's leadership, who must weigh scientific potential against operational hazards, balance the interests of various stakeholders, and navigate complex bureaucratic and political constraints. As of today, October 31, 2025, NASA has not officially sanctioned the Juno maneuver. The designated date for the initial burn, September 9th, remains undecided. Time is rapidly diminishing. Each passing day without a decision renders the opportunity increasingly difficult to seize. Spacecraft trajectories are not infinitely adaptable. Each maneuver has an optimal timing. Missing this window escalates the required delta V, magnifies the risks, and diminishes the probability of success. The September 9th date holds significance for another reason. It falls a mere 8 days prior to Juno's originally scheduled termination date. Should NASA approve the Thursarker's Atlas flyby, it would implicitly signify that the spacecraft will not be deorbited as planned, thereby committing to an extended mission. And if the engine fails to fire, or if unforeseen issues arise, the agency would face scrutiny for having risked Juno on what critics might label a futile endeavor. However, there is a compelling counter-argument, one consistently articulated by Loeb and his colleagues. If we do not attempt it, we learn nothing. 3I Atlas will transit Jupiter in March 2026, irrespective of Juno's observation. It will continue its journey out of the solar system, never to return, carrying with it any secrets it holds. This represents our sole opportunity to study this object at close range with a spacecraft. If we forfeit this chance due to excessive risk aversion or bureaucratic rigidity, what does that convey about our priorities? What does it imply about humanity's resolve to pursue knowledge even when it demands courage and adaptability? The March 16th flyby transcends the singular focus on 3I Atlas. It is instrumental in establishing a precedent for future encounters. In the coming decades, we anticipate encountering more interstellar visitors. Some will pass nearer to Earth, others farther away. Certain events will be detected months in advance, allowing for the planning of dedicated missions. Others will materialize with minimal warning, offering only brief observational windows. Our response to 3I Atlas will inform our approach to subsequent interstellar arrivals. If we successfully redirect Juno, if the spacecraft acquires valuable data, and if we demonstrate the adaptability of existing missions for studying interstellar objects, this sets a powerful precedent. It signifies our agility, opportunism, and willingness to seize unforeseen chances. Conversely, if we fail to act, if bureaucratic caution and risk aversion prevent us from even attempting the observation, that too establishes a precedent. It suggests our space program is inflexible, incapable, or unwilling to adapt to new discoveries, prioritizing the avoidance of failure over the pursuit of groundbreaking scientific advancements. The Juno decision also carries weight due to potential events at perihelion. If 3I Atlas exhibits unusual behavior while obscured by the Sun, such as maneuvering, releasing probes, or displaying phenomena inexplicable by natural means, the March flyby assumes even greater critical importance. It would present our only chance to gather definitive data on an object that has already defied our established models. However, if no anomalies occur at perihelion and 3I Atlas behaves precisely like a typical comet, the March observation remains valuable for understanding the composition and structure of an ancient interstellar visitor. This confluence of unknowns renders the decision exceptionally challenging for NASA. They are being asked to commit resources based on incomplete information. They are unaware of the events at perihelion. They do not know how active 3I Atlas will be in March, its brightness, or the ease of observation. They are being asked to undertake a calculated risk, to wager on the possibility that this object warrants the effort and expense of redirecting Juno. From a purely scientific perspective, the gamble is justifiable. The potential rewards are immense, and the costs are comparatively modest. Juno's mission was nearing its end regardless. Utilizing it for one final endeavor, one last observation, one more contribution to human knowledge before its fiery descent into Jupiter's atmosphere, appears to be the obvious choice. However, organizations like NASA do not operate solely on the principles of pure scientific logic. They function within intricate political, financial, and institutional constraints that do not always align with scientific recommendations. Thus, we wait. We observe. We hope that the engine will ignite, that Juno will be redirected, and that in March 2026 we will obtain our most comprehensive, and perhaps only, close-up view of 3I Atlas. But if this does not transpire, if NASA deems the risks to outweigh the rewards, if funding cannot be secured, or if any other obstacle prevents the flyby, Juno will adhere to its original plan. It will complete a few more orbits of Jupiter, gathering the final fragments of data from its primary mission. Subsequently, on a date in late September, it will plunge into the planet's atmosphere, incinerating like a meteorite, its work concluded. Meanwhile, 3I Atlas will pass Jupiter in March, at a distance of 53.6 million kilometers, unobserved by any spacecraft, its enigmas intact, drifting back into the interstellar void, leaving behind only the questions we were too cautious to explore. Chapter 10. The Thick Disk Origin. Mystery. Envision an entity predating Earth, predating the Sun, and by billions of years, predating the entire solar system. An ancient traveler that coalesced when the universe was nascent, when galaxies were still forming, and when the primordial generation of heavy elements was just beginning to infuse the interstellar medium. Now, imagine that entity traversing our solar system presently, close enough for scientific scrutiny, carrying within its very fabric the imprint of conditions that existed long before anything in our local cosmic vicinity came into being. Such is the potential nature of 3I Atlas. The evidence suggesting its extraordinary antiquity stems from trajectory analysis. By tracing the object's path backward through the galaxy, accounting for the gravitational influence of stars and the overall rotation of the Milky Way's disk, one can infer its point of origin and duration of travel. Matthew Hopkins of the University of Oxford, alongside his collaborators on the Otatai Oxford team, conducted this analysis shortly after 3I Atlas's discovery. Their findings were remarkable. 3I Atlas likely originated from the Milky Way's thick disk. If this is accurate, its age could range between 7 and 11 billion years, possibly more. This would make it older than any comet humanity has ever studied, older than the planetary systems we are familiar with, a genuine relic from the early epochs of galactic history. To grasp the significance of this, one must understand what the thick disk represents. Our galaxy possesses a distinct structure. It is not a random amalgamation of stars, but an organized system comprising disparate stellar populations. The most apparent feature is the thin disk, a relatively planar region, approximately 1,000 light-years thick, where the majority of galactic star formation occurs. Young stars, rich in heavy elements, orbit the galactic center in predominantly circular paths. The Sun resides within the thin disk, as do most of the stars visible to the naked eye at night. However, surrounding and pervading the thin disk is another stellar population, the thick disk. These stars are older, metal-poor, and their orbits carry them on trajectories perpendicular to the galactic plane, extending thousands of light-years above and below the central plane. These stars formed billions of years ago, when the Milky Way was younger, smaller, and less chemically enriched. They represent a different phase of galactic evolution, a period when conditions diverged significantly from those observed in the thin disk today. 3I Atlas exhibits a vertical velocity component, a motion transverse to the galactic plane, consistent with thick disk objects. When its trajectory is extrapolated backward, it does not remain confined to the thin disk, as would most interstellar visitors. Instead, it ventures significantly above and below the galactic midplane, oscillating through a considerably larger volume of space. This vertical excursion is indicative of an ancient object, one that has undergone gravitational interactions over billions of years, gradually accumulating random velocity perturbations that propel objects into thicker, more diffuse orbits. The implications are profound. If 3I Atlas is indeed a thick disk object, it originated from the vicinity of a star that no longer exists, or if that star persists, it is so distant and ancient as to be unrecognizable compared to our Sun. Thick disk stars are metal-poor because they formed prior to multiple supernova generations, enriching the interstellar medium with heavy elements. This suggests that 3I Atlas, if it is a comet, would have formed in a chemical environment vastly different from that of solar system comets. Comets within our solar system contain water ice, carbon dioxide, methane, ammonia, and complex organic molecules, all products of a relatively metal-rich nebula, the cloud of gas and dust that collapsed to form the Sun and planets approximately 4.6 billion years ago. However, a comet originating from the thick disk would have formed in a much more pristine environment. It would possess less carbon, less nitrogen, and fewer of the heavy elements we commonly encounter. Primarily, it would consist of hydrogen, helium, and any oxygen capable of forming water with hydrogen. This raises a crucial question. If 3I Atlas is so ancient and formed in such a dissimilar environment, why does it present as a typical comet? Why does it exhibit a coma and tail, outgas volatiles, and behave in ways familiar from studying objects within our own solar system? Should not 7 billion years of cosmic ray bombardment and micrometeorite impacts have rendered its surface unrecognizable? Should not the harsh conditions of interstellar space have stripped away its volatiles, leaving only refractory materials? The answer may lie in our underestimation of how well-preserved interstellar objects can remain. Outer space is frigid, colder than any terrestrial freezer, hovering around 3 Kelvin, the temperature of the cosmic microwave background radiation. At such temperatures, chemical reactions effectively cease. Volatiles do not sublimate, and ice retains its stability comparable to rock. An object drifting through the galaxy, far removed from any stellar influence, would experience minimal heating, erosion, or degradation. It would simply persist, frozen in time for eons. Only upon entering the inner solar system and approaching the Sun would 3I Atlas begin to warm. Its surface would heat, volatiles would sublimate, and consequently, after billions of years of dormancy, it would become active. It would appear as a comet because it is, in fact, a comet, an astonishingly ancient one that has been in cryogenic storage for the majority of cosmic history. However, a complication has emerged. Recent analysis conducted by a team led by Xavier Perez Couto from the Universidad de Da Coruña suggests that 3I Atlas might not, in fact, originate from the thick disk. Their investigation traced its trajectory backward through 4 million years of galactic history, scrutinizing every star in the solar neighborhood that could have gravitationally influenced its path, yet they found no correlation. None of the proximate stars could account for 3I Atlas's current trajectory. None had perturbed, deflected, or ejected it. The object appears to have been traversing its present path for an extensive period, unaffected by local stellar encounters. This observation led Perez Couto's team to propose an alternative origin, not the thick disk proper, but rather the transitional zone between the thin and thick disks. This frontier region is characterized by the intermingling of stellar populations, where ancient stars from the thick disk orbit alongside younger stars from the thin disk. Within this interpretative framework, 3I Atlas remains ancient, potentially 10 billion years old. However, it did not emanate from the deep recesses of the thick disk, but from its periphery, a region where galactic evolution is complex and not fully understood. This scenario might actually be more scientifically compelling than a purely thick disk origin. The transition zone represents the intersection of the Milky Way's nascent history with its more recent evolutionary stages. Objects originating from this zone carry information pertaining to both eras, shedding light on the processes that shaped the thick disk and those that subsequently formed the thin disk. The study of such an object offers a glimpse into galactic structure and history that cannot be obtained from objects born within a single population. Nevertheless, this interpretation introduces uncertainty regarding the object's precise age. If 3I Atlas originates from the transition region, its age could be anywhere between 7 billion and 10 billion years, or even within a broader range. This ambiguity arises because we lack precise data on the conditions within that region or the timing of star formation there. Our current estimates are based on educated conjecture derived from galactic models and statistical reasoning rather than direct measurements. What is truly needed is a chemical analysis. If we could determine the isotopic ratios of elements within 3I Atlas, quantify the abundance of various molecules, and compare its composition to that of solar system comets and theoretical predictions for primordial material, we could establish its age and origin with far greater accuracy. This is precisely the objective of the James Webb Space Telescope observations conducted in August and December. However, as is the case with many facets of this investigation, the data are still undergoing analysis, and the results have yet to be published, leaving us in a state of informed speculation rather than definitive knowledge. The question of age is significant for several reasons. Firstly, it influences the probability of 3I Atlas being of technological rather than natural origin. If it is 7 billion years old, it would have been constructed by a civilization that emerged billions of years before humanity and billions of years before Earth itself existed. While not impossible, this is statistically less probable than an object originating from a more recent epoch. Greater age implies greater rarity, and consequently, fewer opportunities for civilizations to have manufactured it. Secondly, the age impacts our interpretation of the object's trajectory. An aged celestial body would have endured billions of years of gravitational shifts, chance encounters with stellar bodies and interstellar gas clouds, and unpredictable orbital changes. Its present trajectory through our solar system could be largely arbitrary, a consequence of innumerable minor deviations accumulated across cosmic epochs. Conversely, a younger object, perhaps only a few 100 million years old, would exhibit a path more intimately connected to its originating star. Its course could be charted with greater certainty, potentially even pinpointing the precise stellar system from which it originated. Thirdly, the age of an object significantly influences what can be gleaned about planetary genesis and the broader evolution of galaxies. A comet aged 7 billion years represents a direct sample of the raw materials present in the Milky Way during what astronomers refer to as the cosmic noon, a period of intense star formation when galaxies were at their zenith of activity. This was a fundamentally different universe, smaller, more densely packed, and inherently more volatile. Examining materials from that era provides empirical validation for theoretical frameworks explaining how galaxies coalesce and develop. A comet 10 billion years old is even more remarkable. 10 billion years ago, the universe itself was a mere 3.7 billion years old. Galaxies were still in their nascent stages. The Milky Way had not yet assumed its current configuration. Any planetary systems that formed during that primordial epoch would have been constructed from matter that was virtually unadulterated, with minimal enrichment from preceding stellar generations. If 3 Atlas possesses such an advanced age, it transcends the classification of a mere comet. It is an archaeological relic from the dawning of galactic complexity. However, it is here that the discussion takes a philosophically intriguing turn. If 3 Atlas is indeed billions of years old, and if intelligent life can emerge around ancient stars, then it is at least conceivable that this object encountered, or was intentionally crafted by, intelligences that predate humanity by unfathomable gulfs of time, not thousands or even millions of years, but billions. Civilizations that might have risen, thrived, and subsequently vanished or transformed into something utterly unrecognizable long before our own sun ignited. This presents a variation of the zoo hypothesis that is rarely contemplated. It is not the notion that nascent civilizations like ours are under observation by contemporary extraterrestrials, but rather the idea that our galaxy has been inhabited and re-inhabited repeatedly across billions of years. It suggests that the Milky Way is profoundly ancient and that intelligence has emerged countless times throughout its history, each instance leaving behind enduring traces, artifacts, or structures that persist long after the civilizations themselves have ceased to exist. If this perspective holds true, then the technological nature of 3 Atlas does not necessitate its recent origin, nor even an origin a million years ago. It could be a probe dating back a billion years, an autonomous explorer from a defunct civilization still fulfilling its directives long after its creators have crumbled to dust. Alternatively, it might be a 10-billion-year-old remnant of a galactic framework that is beyond our current comprehension, a piece of archaic engineering drifting through space because its original purpose has been obsolete for millennia. This scenario might sound like science fiction, and indeed, it likely is. However, the age of 3 Atlas compels us to acknowledge the reality that our galaxy has existed for an immense duration, and the history of intelligent life within it could be far more extensive and intricate than we currently assume. By categorizing every anomalous object as necessarily recent, as invariably linked to extant civilizations, we impose human temporal scales upon processes that operate on cosmic timescales, which represents a profound conceptual miscalculation. Consequently, the mystery of the thick disk's origin is not solely about the provenance or age of 3 Atlas. It is about broadening our conceptual horizons to encompass the possibility that some of what we observe within the galaxy is not contemporary, but profoundly ancient. It implies that we might be encountering relics rather than active phenomena, fossils rather than living organisms. If 3 Atlas is such a relic, truly 7 or 10 billion years old, then the anomalies we are scrutinizing assume a different character. They may not necessarily be indicative of recent extraterrestrial activity. They could instead be evidence of extremely ancient alien endeavors, of engineering undertaken so far in the past that the very concept of its originators and their motivations becomes almost irrelevant. More plausibly, however, they might represent natural phenomena that we do not yet fully comprehend, such as cometary behavior under extreme conditions, or physical processes that manifest only in objects that have spent billions of years traversing interstellar space. The universe is inherently strange and prone to surprising us. The mere fact of an object's antiquity does not inherently signify artificiality. Nevertheless, in either interpretation, the age of 3 Atlas is of paramount importance. It recontextualizes the inquiry and compels us to consider extended timescales, to explore possibilities that lie beyond our conventional assumptions. Ultimately, this is what imbues this object with such significant value, not because it is definitively alien or natural, but because it challenges us to expand our understanding of the cosmos and our place within it. 3 Atlas is revealing to us that our galaxy is older and more complex than our limited perspective from our own solar system typically acknowledges. It demonstrates that objects can endure for durations that vastly exceed the span of human civilization. It underscores that the Milky Way possesses a profound history, and that fragments of that history occasionally traverse our cosmic vicinity, offering us fleeting opportunities to study eras that would otherwise remain eternally inaccessible. Regardless of whether its origin is natural or technological, whether it is 7 or 10 billion years old, or whether it originated from the thick disk or the transitional zone, 3 Atlas serves as a messenger from the distant past. Its message is simple. The galaxy you inhabit is ancient. It has witnessed occurrences that defy your imagination, and occasionally with patience, vigilance, and a measure of luck, it offers you a reminder of the vastness of what has come before.